What if everything you know about time, space, and reality is just an illusion? Imagine a universe where the past, present, and future coexist, and our existence is merely a projection. Join us as we explore groundbreaking discoveries that challenge the very fabric of the cosmos. We'll unravel the mysteries of time, delve into the secrets of light speed, and rethink gravity's role in the universe. Interestingly, our journey to understanding time has been a tapestry woven through centuries of observation, philosophy, and scientific revolution. Ancient civilizations, such as the Egyptians and the Greeks, observed the cyclical patterns of the heavens. They saw time as a series of recurring events based on the rhythmic dance of celestial bodies, the sun, the moon, and the stars. For instance, the Egyptians divided the day into two 12-hour periods based on the shadow cast by the sun, and their intricate calendars were firmly rooted in their agricultural cycles. The Greeks, philosophers like Plato and Aristotle, pondered time as a constant linear progression, a series of countless nows that march endlessly forward. For these early thinkers, time was more qualitative, woven deeply into the fabric of life and the seasons. Fast forward to the 17th century, and our understanding of time underwent a dramatic transformation with Isaac Newton's groundbreaking work in classical mechanics. Newton described time as an absolute entity, a steady, unchanging backdrop against which the events of the universe unfolded. This notion stood unchallenged until the dawn of the 20th century, when Albert Einstein introduced his theory of relativity, forever altering our perception of time. According to Einstein, time is not a constant, but is intertwined with the fabric of space itself, forming what we now call space-time. In his view, time can stretch and compress depending on the velocity at which an observer is moving, and the presence of massive objects like stars or planets can bend this space-time continuum. This revolutionary idea has not only deepened our understanding of the cosmos, but has also opened doors to exploring profound concepts like time dilation and the possibility of time travel, suggesting that time, once thought of as rigid and unyielding, is far more flexible and fluid than previously imagined. Imagine you and your best friend decide to take a trip. You stay on Earth, doing your usual activities, while your friend embarks on a high-speed adventure aboard a hypothetical spaceship that zips close to the speed of light. Let's give your friend a playful nickname, say, Speedy Sam. Now, while you're busy binge-watching your favorite shows and lounging around, Speedy Sam is jetting off at mind-boggling speeds, exploring distant corners of the galaxy. 1 year passes for you on Earth, but when Speedy Sam returns, you're amazed to discover that for them, only a few months have elapsed. This curious phenomenon is known as time dilation, a concept predicted by Albert Einstein's theory of relativity. It's as if Speedy Sam has a magic watch that runs slower compared to yours, simply because of the high velocity at which they traveled. This effect is not just science fiction, it's actually been observed with precise atomic clocks on airplanes and satellites, which tick slightly slower compared to those on Earth. Visualize this. You're like a leisurely snail, ambling along and experiencing time normally. Meanwhile, Speedy Sam, the superfast jet setter, is like a blur of motion, zipping by and experiencing time more slowly. This mind-bending aspect of physics shows that time, something we often think of as steady and universal, can stretch and compress depending on how fast we're moving. So, next time you and Speedy Sam plan a trip, remember, the faster you go, the slower you age. Or at least, that's how it would seem from the perspective of us earthbound snails. When scientists refer to time as an illusion, they are delving into one of the most intriguing and abstract concepts in physics and philosophy. This idea suggests that our everyday experience of time, past, present, and future, might not reflect the true nature of reality. To understand this, let's dive into what they're getting at. In our daily lives, we perceive time as a linear progression. Moments flow from one to the next, forming a seamless stream from past through present to future. This notion is deeply ingrained in our consciousness, influenced by the arrow of time marked by entropy, the tendency for things to move from a state of order to disorder. However, according to Einstein's theory of relativity, time is not an absolute construct, but rather interwoven with the fabric of space in what he termed space-time. In this framework, all moments in time exist simultaneously. Imagine the universe as a loaf of bread. Each slice represents a moment in time. From this higher dimensional perspective, every event, past, present, or future, simultaneously exists, challenging the very idea that time flows. Further diving into the quantum realm, physicists encounter even more perplexing aspects of time. Quantum mechanics suggests that on the smallest scales, the deterministic flow of time breaks down. Phenomena such as entanglement imply that particles can be correlated in ways that don't fit our traditional understanding of sequential time. This leads some scientists and philosophers to argue that time is a construct of human consciousness, a way our brains order events to make sense of the world. It's like a movie reel, where all frames exist at once, but we perceive them in a sequence. So, when scientists say time is an illusion, they're inviting us into a mind-expanding exploration of a reality where our conventional sense of past, present, and future might just be a useful fiction, a way to navigate a universe far more intricate and interconnected than we can easily comprehend. This perspective doesn't invalidate our everyday experiences, but enriches our understanding, nudging us to reconsider our place in a vast, complex cosmos, where time is not as straightforward as ticking seconds on a clock. The theory of relativity, introduced by Albert Einstein, fundamentally reshapes our perception of time by revealing its fluid and interconnected nature with space. To appreciate this transformation, let's imagine two distinct travelers. One is grounded on Earth, while the other embarks on a journey through the cosmos in a high-speed spaceship. Einstein's theory posits that time, far from being the immutable and universal constant we often assume, is actually flexible and relative, dependent on an observer's speed and gravitational environment. Consider the concept of time dilation, a direct consequence of the theory of relativity. For our Earth-bound traveler, time marches forward at a regular pace. However, for the astronaut traveling at speeds approaching that of light, time slows down compared to their counterpart on Earth. When the astronaut returns from their voyage, they may have aged just a few years, while decades have passed on Earth. This phenomenon isn't merely theoretical. It has been confirmed by experiments with highly precise atomic clocks flown on jets and orbiting satellites, which show measurable differences in elapsed time compared to those on the ground. Einstein's general theory of relativity reveals that gravity can warp both space and time, a concept known as space-time curvature. Massive objects like planets and stars create curves in space-time, causing time to slow down in their vicinity. Imagine holding a stretchy fabric with a weight in the middle. The weight creates a dip, illustrating how space-time bends around massive objects. This curving effect has profound implications. A clock placed near a massive object such as Earth ticks slower than one far away in weaker gravitational fields. This effect is essential for the functionality of Global Positioning System (GPS) satellites, which must account for the differences in time experienced on Earth's surface versus in orbit, to provide precise navigation data. The theory of relativity revolutionizes our understanding of time by demonstrating it is not a fixed background entity. Instead, time is an elastic dimension intertwined with space, capable of stretching, compressing, and bending in response to speed and gravity. This revelation prompts us to rethink time not as a steady, inexorable march, but as a dynamic relative experience, varying according to one's frame of reference within the grand tapestry of the universe. Experiencing time at different speeds, a phenomenon known as time dilation, is one of the more mind-bending predictions of Einstein's theory of relativity. Though the effect is minuscule at everyday speeds, it's been proven through precise experiments and is more pronounced at velocities approaching the speed of light. To make it relatable, let's take a closer look at a scenario involving a fast plane versus standing still on Earth. Imagine you're at an airport, watching planes take off and land. You remain stationary, sipping your coffee. Meanwhile, a jetliner roars down the runway and ascends into the sky. According to relativity, time ticks just a bit more slowly for the passengers on that fast-moving plane compared to you standing still. This isn't about the subjective feeling of time. Those passengers won't notice anything unusual as they chat, read, or nap. But from your grounded perspective, the clocks on the plane run slightly slower than your watch. To add some real-world evidence, Let's delve into a famous experiment conducted in the 1970s known as the Hafel-Keating experiment. Scientists synchronized 4 atomic clocks, 2 of which were flown around the world on commercial jets, one eastward and one westward, while the remaining 2 stayed on the ground. Upon returning, the airborne clocks displayed a deviation from those left behind, consistent with predictions made by the theory of relativity. The clocks on the planes had indeed ticked at a marginally different rate due to their velocities and the gravitational differences encountered at altitude. Even more impressively, this time dilation effect is essential for the functionality of the Global Positioning System, GPS. GPS satellites orbit the Earth at high speeds and are subject to weaker gravitational fields than those experienced on the surface. Engineers must account for both the special relativistic time dilation due to the satellite's speeds and the general relativistic time dilation due to their altitude. Without these corrections, navigational data from GPS would quickly become inaccurate, highlighting how our understanding of time's flexibility underpins modern technology. So, while you may not feel the discrepancy sipping that airport coffee compared to a high-speed plane passenger, relativity assures us that these differences are real, tangible, and measurable. Time, in the grand tapestry of the universe, is not a rigid constant, but a dynamic, relative experience, slightly altered by our speed and location in the gravitational landscape. If we could travel at the speed of light, our perception of time would undergo a dramatic transformation, bordering on the surreal. According to Einstein's theory of relativity, as an object's speed approaches the speed of light, time for that object slows down relative to an external observer. This effect, known as time dilation, becomes so extreme at the speed of light that time would essentially come to a standstill for the traveler. To illustrate, imagine you are an intrepid astronaut preparing for an extraordinary journey aboard a sleek spaceship capable of reaching light speed. As you accelerate, incredible things begin to happen from the perspective of those left behind on Earth. Time for you on the spaceship starts to slow down relative to everyone else. By the time you reach a velocity astonishingly close to the speed of light, a second on your clock might correspond to years, decades, or even centuries on Earth. Now let's push this scenario to the limit. Imagine you could reach the speed of light, something currently deemed impossible for objects with mass. In this extreme case, time for you would theoretically freeze. From your perspective, you could traverse the vast expanses of the galaxy instantaneously. Entire lifetimes or epochs would pass on Earth in what to you would feel like an instant. Stars would age, and civilizations might rise and fall, all while you experience no passage of time at all. This peculiar outcome arises because, at the speed of light, the equations governing relativity predict that moving clocks would stop altogether. However, nature imposes a cosmic speed limit, with light speed being unattainable for objects with mass. To accelerate an object with any mass up to light speed would require infinite energy, a practical impossibility given our current understanding of physics. Even so, this theoretical journey paints a vivid picture of the incredible relationship between speed and time in our universe. So, while real-world light-speed travel remains within the realm of science fiction, exploring these concepts deepens our appreciation of the universe's intrinsic elegance and complexity. Indeed, at the speed of light, time ceases to be a measure of our experience, becoming a fascinating window into the relativistic nature of reality. Black holes are some of the most extraordinary objects in our universe, possessing a gravitational pull so intense that they dramatically warp both time and space around them. This warping arises from the immense mass concentrated into an incredibly small area, leading to significant distortions in the fabric of space-time, as predicted by Einstein's general theory of relativity. Picture space-time as a flexible rubber sheet. If you place a heavy ball in the center, it creates a noticeable dip in the sheet. The heavier the ball, the deeper the dip. A black hole is like an extremely dense ball that creates such a profound dip that it essentially forms a bottomless pit. In this analogy, the closer you get to the edge of this pit, the event horizon, the stronger the gravitational pull. The event horizon is the point beyond which nothing, not even light, can escape the black hole's gravitational grip. As you approach a black hole, several astonishing effects occur. Time dilation becomes extraordinarily pronounced in the vicinity of the event horizon. Suppose an astronaut, let's call them Voyager Vicky, decides to explore near a black hole. From Vicky's perspective, time might seem to flow normally. However, an observer watching from a safe distance would see Vicky's clock slow down dramatically as she nears the event horizon. If Vicky were to hover just outside the event horizon, she might experience only a few moments, while years or even centuries could pass for the distant observer. To viewers far away, Vicky would appear to be frozen in time, perpetually on the brink of crossing into the black hole. Additionally, the warping of space near a black hole creates some of the most fascinating and extreme gravitational effects known to science. Objects that venture too close are stretched and compressed in a process whimsically termed spaghettification. This effect arises because the gravitational pull on the side of the object nearest to the black hole is immensely stronger than on the side farther away, literally elongating objects into thin, spaghetti-like shapes. These incomprehensible distortions of space and time are not merely theoretical musings. They are backed by many lines of astronomical evidence and play key roles in phenomena observed around black holes, such as the extreme gravitational lensing of light, where light bends around the black hole, creating mirage-like images. Moreover, the radiation detected as matter accelerates and heats up while being pulled into a black hole provides crucial insights into these cosmic giants' mysterious nature. Black holes serve as natural laboratories, allowing us to explore the outer edges of physics and our understanding of the universe. By warping time and space so profoundly, they illuminate the workings of gravity in the most extreme conditions, inspiring both awe and scientific curiosity. The notion of traveling back in time has long fascinated humanity, gracing the pages of science fiction and sparking scientific debates for over a century. While captivating, the idea treads a fine line between the realms of theoretical physics and the seemingly impossible. Let's dive into the scientific conversation around this tantalizing possibility. Einstein's theory of relativity allows for some intriguing scenarios where time travel, specifically to the past, could be conceivable. One such concept involves wormholes, hypothetical tunnels in the fabric of space-time that might connect distant points in space and time. Think of space-time like a sheet of paper. Fold the paper so that 2 points touch, and piercing through them with a pencil creates a shortcut or wormhole. If one end of a wormhole could be accelerated to near-light speed or placed in a strong gravitational field and then brought back near the other end, the time dilation effects could theoretically result in a situation where traveling through the wormhole could allow passage to an earlier time. Another concept involves the idea of closed time-like curves, which are solutions to the equations of general relativity that permit paths in space-time to loop back on themselves. Such paths could, in theory, allow an object to return to its own past. Some researchers suggest that rotating black holes or certain cosmic strings, infinitely long, narrow, and incredibly dense objects, could create conditions ripe for these closed, time-like curves. However, these theoretical possibilities come with myriad challenges and paradoxes. One significant issue is the grandfather paradox. Imagine you travel back in time and alter something crucial, such as preventing your grandfather from meeting your grandmother. This act would prevent your own existence, creating a logical inconsistency. Proposed solutions to this paradox include the idea of parallel universes or branching timelines, where changes in the past create alternate realities rather than altering the existing one. Moreover, our current technological capabilities and understanding of quantum mechanics present substantial barriers. For one, creating or stabilizing a wormhole, if they exist, is far beyond our present means. Additionally, the effects of quantum fluctuations and potential need for exotic matter with negative energy density to keep a wormhole open introduce enormous practical and theoretical obstacles. Many physicists, including the eminent Stephen Hawking, have posited concepts like the chronology protection conjecture, suggesting that the laws of physics might inherently prevent time travel to the past to avert paradoxes and preserve causality. This conjecture implies that while the mathematics may allow for certain time travel scenarios, the natural world might have built-in safeguards against such occurrences. In summary, while time travel to the past presents endless intrigue and some tantalizing theoretical frameworks, it remains an elusive concept fraught with paradoxes and practical impossibilities. Scientists continue to explore the intricacies of space-time, and these explorations enrich our understanding of the universe. Yet for now, the time machine remains firmly entrenched in the realm of imagination and theoretical speculation. Movies and TV shows often depict the concept of time travel in ways that captivate audiences but sometimes stretch or outright ignore the boundaries established by physics and logical consistency. While these dramatizations offer riveting narratives, they frequently get several scientific and conceptual aspects wrong. First and foremost, the portrayal of instantaneous time travel is a common trope that falls short of real-world scientific principles. Many of these narratives depict characters stepping into a machine, pressing a button, and immediately finding themselves in a different era. This idea strays far from the theoretical complexities of time travel as suggested by Einstein's theory of relativity, which involves intricate manipulations of space-time involving massive energy inputs, wormholes, or near-light-speed travel. None of these methods would allow for the simple push-button convenience seen in films and TV. Furthermore, the concept of a single, mutable timeline is another frequent inaccuracy. In many stories, characters change events in the past, which directly alters the present or future. This notion clashes with many theoretical considerations, like those found in the block universe model of physics, where all points in time are fixed and unchanging. Changes in the past leading to an altered present introduce significant paradoxes, such as the grandfather paradox, which is rarely satisfactorily addressed. While some shows adopt the many worlds interpretation, creating parallel universes to resolve these paradoxes, these interpretations are seldom explored with the depth necessary to reflect the true complexity of quantum mechanics and multiverse theories. A glaring oversimplification in entertainment is the depiction of time travel without consideration of Earth's movement through space. Our planet is continuously orbiting the Sun, and the Sun itself is orbiting the center of the Milky Way galaxy. Therefore, even if one could theoretically move through time, they would also need to account for the spatial relocation required to end up in the same geographical spot. Most movies and TV shows ignore this dynamic, presenting time travel as if it occurs in a fixed spatial location. Finally, time travel narratives often skirt around the immense energy requirements and technical barriers involved. In reality, the energy needed to manipulate space-time to the extent required for time travel would be astronomical, far beyond anything conceivable with current technology. The manipulation of space-time might also involve high levels of radiation or exotic forms of matter, none of which are addressed in the often sanitized depictions on screen. While movies and TV shows get time travel wrong from a scientific standpoint, their inaccuracies allow for more engaging, imaginative storytelling. They provide a platform for exploring human emotion, moral dilemmas, and the boundless curiosity that drives us to ponder the nature of time. While these portrayals often sidestep scientific rigor, they succeed in captivating audiences and sparking interest in deeper questions about the universe, questions that science continually strives to answer. Several famous experiments have tested the nature of time, providing critical insights into its elusive characteristics. These experiments range from testing the effects of time dilation, as predicted by Einstein's theory of relativity, to investigating quantum mechanics' peculiarities. Here are some of the most notable ones. The Huffle-Keating experiment. Conducted in 1971, this experiment involved flying 4 atomic clocks on commercial airliners around the world in both eastward and westward directions. 2 synchronized atomic clocks were kept at the U.S. Naval Observatory for reference. Upon landing, the airborne clocks were compared with the reference clocks. The results showed that the airborne clocks had experienced time differently, corroborating both special relativity, due to their high velocity, and general relativity, due to differences in gravitational potential. The eastward flying clocks exhibited a slightly slower elapsed time compared to the reference clocks, while the westward flying clocks showed a slightly faster elapsed time, matching relativity's predictions. The twin paradox. While more of a thought experiment than a physical one, the twin paradox is a staple illustration of time dilation described by special relativity. It imagines one twin traveling to a distant star at near light speed, while the other remains on Earth. Upon returning, the traveling twin finds they have aged less than the twin who stayed behind, due to the effects of time dilation experienced during high-speed travel. Though no human has yet taken such a journey, tests involving fast-moving particles have confirmed the principles behind this paradox. The Pound-Rebka experiment. Conducted in 1959 by physicists Robert Pound and Glenn Rebka at Harvard University, this experiment tested gravitational time dilation, the effect of gravity on the passage of time. Using the Mossbauer effect, which involves the emission and absorption of gamma rays by ion nuclei without loss of energy, they measured the shift in frequency of gamma rays traveling upwards through a vertical height in Earth's gravitational field. The results aligned with predictions from general relativity, confirming that clocks run slower in stronger gravitational fields. The GPS system. While not an experiment in the traditional sense, the Global Positioning System, GPS, provides practical, ongoing verification of relativity. GPS satellites orbit Earth at high speeds and experience weaker gravity compared to clocks on the ground. Engineers must account for the resulting time dilation effects, both from special and general relativity, to ensure the system's accuracy. Without these relativistic adjustments, the system would quickly become inaccurate, deviating by several kilometers each day. The Large Hadron Collider, LHC. While largely known for particle physics discoveries, experiments at the LHC have inadvertently tested aspects of special relativity. Particles accelerated to near-light speeds exhibit time dilation and increased lifespans compared to when they are at rest. For instance, unstable particles known as muons created in high-energy collisions live significantly longer when moving at relativistic speeds, aligning with relativistic predictions. These experiments highlight the intricate and fundamental nature of time as described by modern physics, validating Einstein's groundbreaking work and extending our understanding of the universe. While these tests underscore the relative and flexible character of time, they also open doors to new questions, encouraging further exploration into one of the most fascinating dimensions of our reality. The arrow of time is a concept in physics and philosophy that describes the one-way direction or asymmetry of time. It refers to the common observation that time seems to flow in a single irreversible direction, from the past through the present and into the future. From the past through the present and into the future. This unidirectional flow significantly influences our daily lives and our understanding of the universe. Let's delve into the concept and its implications. One of the primary foundations for the arrow of time is the second law of thermodynamics, which states that the entropy, or disorder, of an isolated system always increases over time. In simple terms, entropy measures the number of ways a system can be arranged, and higher entropy corresponds to higher disorder. For example, imagine a glass shattering on the floor. The glass pieces scatter, increasing the overall entropy. The process proceeds in one direction, glass to shards, not the reverse. This law of increasing entropy provides a clear distinction between the past and the future, manifesting the arrow of time. In our everyday life, the arrow of time guides our sense of causality. Events have causes that precede them and effects that follow. We wake up in the morning and go to bed at night. We eat breakfast before lunch and lunch before dinner. This chronological sequence underpins our scheduling and planning, our memories of past events, and our anticipation of future activities. Our life experiences are deeply rooted in this forward flow of time, giving us a structured way to interpret reality and make sense of the world. Biological processes are also tied to the arrow of time. Our bodies age, and cells undergo cycles of growth and decay, all of which proceed in a single direction. From birth to childhood to adulthood and eventually to old age, the irreversible nature of biological time underscores the temporal progression we experience. Similarly, the natural world around us, trees growing from seeds, rivers carving valleys, and seasonal cycles, all echo this forward-moving temporal direction. Communication and information flow are further guided by the arrow of time. When we speak, write, or convey messages, the information moves from past to present to future. This directional flow ensures coherence and understanding. A letter is written before it is read, decisions are made based on past data, and plans are formed for future action. This temporal progression is essential for meaningful interactions and decision-making. In summary, the arrow of time, rooted in the fundamental laws of thermodynamics and observable across various scales of existence, governs much of our everyday experience. It defines the sequence of events, guides biological and natural processes, and shapes our communication and understanding of causality. This intrinsic aspect of time allows us to organize our lives, learn from the past, act in the present, and prepare for the future, demonstrating the profound impact of the arrow of time on our perception and reality. The philosophical and scientific notion that time might be an illusion can profoundly impact how we perceive and structure our daily lives. While this concept doesn't necessarily alter the physical reality we experience, it invites us to rethink our relationship with time and may lead to shifts in our attitudes, behaviors, and routines. Firstly, if time is considered an illusion, it challenges the deeply ingrained belief in a rigid linear progression from past to present to future. Recognizing the possibility that all moments may exist simultaneously or that our perception of time is a mental construct can foster a greater appreciation for the present moment. This mindfulness can lead to a decreased emphasis on constantly rushing through tasks or anxiously planning for the future and a more profound enjoyment of the here and now. Practically, this might mean incorporating practices like meditation, which emphasize living in the moment, into daily routines. People might become less stressed about meeting deadlines and more focused on the quality of their experiences. Work and leisure could become more balanced as individuals start using time as a fluid concept rather than a relentless sequence of events that must be rigidly managed. Additionally, the idea of time as an illusion could impact how we approach priorities and relationships. If we see each moment as interconnected rather than sequential, the urgency of certain tasks might diminish, encouraging a more holistic, less fragmented view of life. Relationships and social interactions might gain prominence as the importance of shared, meaningful experiences could outweigh the pressure of productivity and time-bound achievements. Our sense of aging and life's milestones could also be influenced. The traditional notion of aging as a linear, inevitable process might give way to a more flexible perspective of personal growth and development, which isn't strictly tied to chronological age. People might focus more on cyclical or non-linear personal progress, reflecting on their lives as a series of enriching experiences, regardless of their position in a timeline. From a broader perspective, re-evaluating time's rigidity could inspire changes in societal structures and norms. Work schedules, education systems, and even healthcare could evolve to accommodate more flexible, humane approaches that reflect the fluid nature of individual lives rather than the strict ticking of the clock. For instance, there could be greater emphasis on results and outputs rather than rigid timelines and deadlines. Businesses and personal productivity tools might innovate to accommodate these new perspectives. There could be a rise in tools designed to help individuals achieve a flow state, balancing productivity with well-being rather than solely focusing on time management. In conclusion, while the scientific and philosophical idea that time may be an illusion doesn't change the observable sequence of events we experience, it invites us to reconsider how we perceive and value time. This shift in perspective can lead to more mindful living, reshaping our daily routines to focus on present experiences, holistic progress, and meaningful relationships. It encourages a balance between efficiency and well-being, helping us create a more fulfilling and enriched existence. The concept of time is interpreted in myriad ways across different cultures and philosophies, reflecting the diverse ways societies understand their place in the universe and the rhythm of life. These interpretations influence many aspects of daily life, social structure, and individual behavior. In Western cultures, heavily influenced by Judeo-Christian traditions and scientific advancements, time is often perceived as linear. This perspective sees time as an arrow moving from past to present to future, emphasizing progress, efficiency, and a forward-looking mindset. This linear concept underpins many aspects of Western life, including work schedules, education systems, and historical narratives, which presume a constant march toward improvement or a specific endpoint. By contrast, many Eastern philosophies offer a more cyclical view of time, rooted in natural cycles and recurring patterns. For instance, in Hinduism, time is perceived as a series of vast cosmic cycles, or yugas, each with its distinct characteristics and duration, eventually leading to a repeating cycle of creation and destruction. This cyclical understanding fosters a sense of continuity and renewal, influencing spiritual practices, agricultural cycles, and festivals tied to the rhythms of nature. Similarly, in Buddhism, the concept of time is intertwined with the doctrine of impermanence and the cycle of birth, death, and rebirth, samsara. Time is seen as fluid and transient, with an emphasis on the present moment and mindfulness. Buddhist practices encourage living in the present and understanding the fleeting nature of existence, leading to a focus on mental discipline and spiritual growth over external progress. Indigenous cultures often have their unique temporal frameworks that are deeply connected to their environments and ways of life. Many Native American cultures perceive time as a more flexible and interconnected web, where past, present, and future are interwoven. Events are often contextualized within stories and traditions that emphasize the cyclical patterns of nature and the importance of community continuity. The Mayan civilization had a sophisticated understanding of time, using multiple calendars to track cosmic and terrestrial cycles. Their long count calendar, for instance, tracks vast epochs of time, while the Tzolk'in and Harb calendars integrate shorter cycles of days and agricultural seasons. This intricate system reflects an integrated view of cosmic and earthly time, guiding religious rituals, agricultural activities, and societal organization. In contemporary philosophy, time continues to be a field of rich exploration. Existentialist philosophers like Martin Heidegger explored time as it relates to human existence, emphasizing being and becoming rather than seeing time as a mere backdrop. Heidegger's focus on Dasein, or being in the world, posits that our experience of time is deeply personal and is linked to our sense of meaning and purpose. Additionally, modern physics and cosmology offer yet another dimension to the interpretation of time. Theories such as Einstein's relativity challenge the notion of absolute time, proposing instead that time is relative and connected to the fabric of space itself. Quantum mechanics introduces even more perplexing views, with phenomena like quantum entanglement defying classical temporal and spatial separations. Overall, the way different cultures and philosophies interpret time provides invaluable insight into how they perceive existence, continuity, and change. Whether viewed as linear, cyclical, or interwoven with space, these temporal frameworks shape how communities organize their lives, make sense of the universe, and find meaning in their experiences. They remind us that time is more than just a measure. It is a fundamental lens through which we understand our reality and our place within it. The block universe theory, also known as the block time theory or the eternalism perspective, provides a unique and somewhat counterintuitive conceptualization of time. It posits that all points in time, past, present, and future, are equally real and exist simultaneously, much like different locations in space. According to this view, the universe can be imagined as a four-dimensional block where time is just another dimension, similar to the three spatial dimensions. This theoretical framework emerges from Einstein's theory of relativity and offers a profound take on the nature of existence and time. In the block universe, the flow of time as we commonly experience it, moving from past to present to future, is an illusion of human consciousness. Instead, all events, whether they happened yesterday, are happening now, or will happen tomorrow, exist in a complete, unchanging framework. Just as every location on a map exists simultaneously, every moment in time exists simultaneously within the block of the universe. To visualize this, imagine holding a block of marble. You could inscribe a timeline along the length of the block, representing past, present, and future events. From your perspective, looking at the block as a whole, all these events are visible at once. An inhabitant inside this block, however, experiences time sequentially, just as we do in our daily lives. This analogy helps illustrate how the block universe envisions time, a dimension where every moment is fixed and immutable. Special relativity heavily influences this conceptualization as it intertwines space and time into a single continuum known as space-time. One of the key insights from relativity is that different observers, depending on their relative motion, may disagree on the sequence of events or whether two events happen simultaneously. This variability suggests that the linear progression of time isn't universal. There's no privileged now moment that is the same for everyone everywhere. Instead, time is relative and depends on the observer's frame of reference. The block universe theory addresses several complex questions about time, causality, and existence. For instance, it sidesteps the paradoxes traditionally associated with time travel. If every point in time is fixed and unchangeable within the block, the idea of altering past events becomes irrelevant. Any time travel that does occur would simply be a journey to different coordinates within this immutable structure. Moreover, the block universe has philosophical implications, particularly regarding free will and determinism. If the future is already laid out just like the past, it raises questions about our ability to influence or change future events. Some interpret this as a deterministic view, where all actions and outcomes are predetermined within the space-time block. Others propose more nuanced interpretations, suggesting that our perception of making choices is a part of our experience within this fixed framework. In summary, the block universe theory provides a fascinating and radically different way of understanding time. By viewing time as an additional dimension in a four-dimensional space-time continuum, it presents a model where all moments exist simultaneously, challenging our everyday perceptions of temporal flow. While this concept is deeply rooted in the principles of relativity, it opens intriguing dialogues on the nature of reality, causality, and human experience. The block universe theory presents a fascinating contrast to our everyday experience of time. In our daily lives, we perceive time as a continuous, flowing entity moving from the past through the present and into the future. We see ourselves as journeying through time, where the present is a fleeting moment and the past is left behind as mere memories. This perception aligns with what physicists refer to as the presentist view, where only the present moment is real and the past and future hold no true existence. In stark contrast, the block universe theory, rooted in Einstein's theory of relativity, suggests a more static nature of time. According to this theory, time is viewed as a four-dimensional block where all moments, past, present, and future, exist simultaneously. In this model, your childhood memories, today's experiences, and even events in the distant future are all embedded in this unchanging four-dimensional space-time continuum. Essentially, time does not flow. Instead, every moment is already laid out, much like the frames of a film reel. This perspective can be mind-boggling, but offers profound implications, allowing us to rethink our place in the universe, where our destiny might be as concrete as our history. The implications of the block universe theory for our understanding of past, present, and future are profound and often challenge our deepest intuitions about time. In the block universe, the distinctions between past, present, and future become less about what is real and more about where events are situated in the four-dimensional space-time fabric. According to this theory, every event that has happened, is happening, or will happen exists simultaneously in a grand tapestry of space-time. This means that the future is as fixed and unchangeable as the past, fundamentally altering our conception of free will and the fluidity of time. For instance, in our everyday experience, the past is seen as immutable and the future as a realm of possibilities. However, in the block universe, both the past and the future are equally determined. Temporal slices of your life, from childhood games to future retirement, are just different coordinates in this fixed structure. This brings into question notions of causality and the flow of time, suggesting that the arrow of time, which we perceive due to entropy and the second law of thermodynamics, might be an emergent property rather than a fundamental feature of reality. As a result, our conventional narrative of time, with its inherent tenses and unfolding events, requires a radical reinterpretation in light of the block universe theory. The block universe theory profoundly impacts our understanding of free will and determinism, casting a deterministic light on the entire temporal landscape. Since in this view, every moment in time, past, present, and future, coexist in a fixed four-dimensional space-time, it implies that the future is as unalterable as the past. This inherently challenges traditional notions of free will, where we believe our present actions can influence our future outcomes. In the block universe, the future is already written. It is embedded in the space-time continuum just as indelibly as historical events. This deterministic framework suggests that all events, including human decisions, are predetermined by the conditions laid out in the fabric of space-time. Our sense of agency, the feeling that we can change our destinies by making different choices, becomes an illusion, as every action and decision is merely a point along the space-time continuum. Some philosophers and scientists argue that this perspective doesn't necessarily negate the experience of making choices. Instead, it reframes our understanding by suggesting that our decisions and actions are part of the intricate and unchangeable tapestry of the universe. While this can be unsettling, it opens up new avenues for exploring the nature of consciousness, the meaning of existence, and the interconnectedness of all temporal events within the cosmological whole. It pushes us to reconsider what it means to make a choice if that choice is as fixed in the timeline as any physical event. Movies and literature often delve into the concept of the block universe, offering audiences imaginative and thought-provoking narratives that challenge our conventional perceptions of time and existence. Films like Interstellar, directed by Christopher Nolan, explore this idea through the lens of advanced physics and human emotion. In Interstellar, the protagonist journeys through a wormhole, experiencing time dilation and ultimately witnessing events from different points in time simultaneously. This cinematic portrayal mirrors the block universe theory, where all moments are interconnected and occur simultaneously within the space-time continuum. The movie beautifully intertwines scientific theory with storytelling, prompting viewers to reconsider the linearity of time. Similarly, literature has long been a fertile ground for exploring the block universe concept. Kurt Vonnegut's novel Slaughterhouse-Five presents a protagonist, Billy Pilgrim, who becomes unstuck in time. He experiences different moments of his life out of sequence, reflecting the block universe's idea that past, present, and future coexist eternally. This narrative technique not only illuminates the theory, but also provides a poignant commentary on human existence, memory, and the nature of time. These artistic explorations allow us to engage with complex scientific ideas in an accessible and emotionally resonant way, blending the boundaries between hard science and imaginative fiction. In doing so, they invite us to ponder the true nature of our reality and our place within the vast tapestry of time. The idea that the universe might be an illusion or might not exist at all has intrigued philosophers, scientists, and thinkers for centuries. One of the most compelling arguments comes from the realm of philosophy, particularly the concept of solipsism, which posits that only one's mind is sure to exist. According to this view, anything outside of one's own consciousness, including the universe, could be an illusion or a construct created by the mind. This line of thought challenges the very fabric of reality, suggesting that our perceptions of the external world may be entirely subjective and unreliable. In modern science, the notion that the universe might be an illusion finds footing in theories from quantum mechanics and cosmology. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that reality only becomes definite upon observation. Until measured, particles exist in a state of superposition, where they can be in multiple states simultaneously. This has led some to argue that the universe is not objectively real, but is instead dependent on observation for its existence. Additionally, the holographic principle in cosmology suggests that the entire three-dimensional universe could be described by information encoded on a two-dimensional surface, much like a hologram. If true, this would upend our conventional understanding of space and reality, and imply that our perceived universe might be more of an intricate projection than a tangible entity. These arguments compel us to question the nature of existence itself, pushing the boundaries of both philosophical inquiry and scientific investigation. While these ideas may seem abstract or speculative, they serve as important reminders of the complexities and mysteries that still surround our understanding of the universe. Whether viewed through the lens of philosophy or advanced scientific theories, the possibility that the universe might be an illusion challenges us to rethink our assumptions about reality and existence. Quantum mechanics, with its utterly counterintuitive principles, substantially challenges our conventional perception of reality. At the heart of quantum mechanics lies the concept of superposition, where particles such as electrons and photons can exist in multiple states simultaneously until they are observed or measured. This is famously illustrated by Schrödinger's cat thought experiment, where a cat in a sealed box is considered to be both alive and dead until someone opens the box to observe it. This superposition principle defies our everyday experiences, where objects have definite states and positions. Further compounding the challenge to our perception of reality is the phenomenon of entanglement. When particles become entangled, their properties become linked, so that the state of one particle instantaneously influences the state of another, regardless of the distance separating them. This spooky action at a distance, as Einstein described it, seems to violate the speed limit set by the speed of light and suggests a non-locality that contradicts classical theories of space and time. Quantum entanglement implies that objects are not as separate as they appear, and that the universe might be an interconnected web of relationships rather than independent entities. Additionally, the wave-particle duality in quantum mechanics posits that particles can exhibit both wave-like and particle-like properties depending on the experimental setup. This duality dismantles the classical view that particles have a fixed nature, instead revealing a context-dependent reality that only becomes concrete under specific conditions. The observer effect, where the act of measurement itself influences the state being measured, further blurs the line between reality and perception. These principles suggest that at the quantum level, reality is not a fixed entity, but a fluid, probabilistic field influenced by observation and interaction. By fundamentally challenging our perceptions of certainty, locality, and discrete objectiveness, quantum mechanics forces us to reconsider the very nature of reality itself. In quantum mechanics, the role of the observer is both pivotal and profoundly enigmatic, bringing into question our basic assumptions about the nature of reality. Central to this is the principle of wave function collapse, which posits that until a quantum system is observed or measured, it exists in a superposition state, wherein all possible outcomes coexist simultaneously. The act of observation causes this superposition to collapse into a single determinate state. This means that the observer, by the mere act of measuring or observing, fundamentally influences the outcome of a quantum event, a concept that stands in stark contrast to classical physics, where systems evolve independently of observation. The famous double-slit experiment exemplifies this phenomenon. When particles such as electrons are fired at a barrier with two slits, they exhibit an interference pattern on a screen behind the barrier, suggesting they behave like waves and go through both slits simultaneously. However, when observers place detectors to see which slit the particles pass through, the particles then behave like particles, and the interference pattern disappears. This demonstrates that observation changes the behavior of particles, forcing them to adopt a definite state. The observer effect raises profound questions about the nature of reality and the role consciousness plays in the universe. Some interpretations, like the Copenhagen interpretation, suggest that physical systems do not have definite properties until they are measured. This infers that reality itself could be, in a sense, co-created by observers. Other interpretations, such as the many worlds interpretation, avoid the need for collapse by proposing that all possible outcomes of a quantum measurement actually occur, but in separate, branching universes. The observer in quantum mechanics is not merely a passive witness, but an active participant in the unfolding of reality. This challenges the classical view of an objective, observer-independent universe, and suggests a more intertwined relationship between consciousness and the physical world, opening up intriguing philosophical and scientific discussions about the nature of existence and the fabric of reality itself. Superposition and entanglement, two fundamental principles of quantum mechanics, profoundly transform our understanding of reality by challenging the rigid deterministic framework traditionally laid out by classical physics. In classical terms, objects are thought to occupy one state at any given time and possess definite properties. Quantum mechanics, however, reveals a world where these certainties evaporate into probabilities and interconnected webs of influence. Superposition refers to the concept wherein a quantum particle, such as an electron, can exist in multiple states or locations simultaneously. Until a measurement is made, the particle is described by a wave function that encompasses all possible states. This notion is vividly illustrated by Schrödinger's cat thought experiment, where a cat in a sealed box is both alive and dead until the box is opened and observed. Superposition challenges the notion of a definite state and forces us to reconsider reality as something more fluid and indeterminate, governed by probability waves rather than fixed outcomes. Entanglement, on the other hand, delves deeper into the connectedness of the quantum world. When particles become entangled, the state of one particle instantaneously affects the state of another, irrespective of the distance separating them. This phenomenon suggests a level of non-locality in the universe, implying that particles are not isolated entities, but part of a larger interconnected system. Einstein famously referred to entanglement as spooky action at a distance, highlighting how it defies the classical notion that objects are influenced only by their immediate surroundings. The implications of superposition and entanglement are monumental. For one, they suggest that reality at the quantum level is far more nuanced and interconnected than our macroscopic experiences suggest. Superposition implies that possibilities reign over certainties until observation intervenes, while entanglement demonstrates a deep intrinsic link between particles that transcends spatial separation. These principles dismantle the classical idea of an objective, observer-independent reality, paving the way for a universe where observation, measurement, and interconnectedness play pivotal roles. These quantum phenomena compel us to rethink notions of locality, causality, and even the fabric of space-time itself. They also fuel philosophical debates about the nature of consciousness and its role in shaping reality. Through the lens of superposition and entanglement, reality emerges not as a static, independent entity, but as a dynamic, interwoven tapestry intricately tied to the act of observation and the fundamental interconnectedness of all things. The holographic principle is a revolutionary concept in theoretical physics, suggesting that all the information contained within a three-dimensional volume of space can be represented on a two-dimensional boundary that encases this volume, much like a hologram. This principle emerged from considerations in string theory and black hole physics, notably through the work of physicists such as Gerard T. Hooft and Leonard Susskind. It proposes that the physics within a spatial region can be fully described by information encoded on the boundary of that region, analogous to how a hologram stores a three-dimensional image on a two-dimensional surface. One of the most compelling pieces of evidence for the holographic principle comes from the study of black holes. According to the laws of black hole thermodynamics, the entropy, or informational content, of a black hole is proportional to the area of its event horizon, not its volume. This unexpected finding led physicists to speculate that the quantum states describing the black hole's interior might reside on its surface. If this can be true for black holes, it raises the possibility that our entire universe could operate under similar principles. Expanding this concept to the universe as a whole, the holographic principle suggests that the reality we perceive in three dimensions, including the passage of time, might actually be a projection from a two-dimensional surface. This surface could be likened to the cosmological horizon or some other larger boundary. If true, this would imply that our perceived reality is akin to a holographic image where the actual reality is encoded on a distant lower dimensional boundary. This paradigm challenges our traditional understanding of space and reality. It posits that the universe might not be as volumetric as it appears, potentially altering how we think about spatial relationships and distances. The holographic principle also dovetails intriguingly with theories of information and computation, suggesting that the universe fundamentally processes and conveys information in ways that transcend our usual three-dimensional experience. The holographic principle also dovetails intriguingly with theories of information and computation, suggesting that the universe fundamentally processes and conveys information in ways that transcend our usual three-dimensional experience. The holographic principle invites us to envision a universe that is fundamentally different from our macroscopic intuitions, a universe where the true nature of reality is encoded on a boundary, and the three-dimensional world we inhabit is a richly detailed projection from this lower dimensional surface. This line of thought serves as a bridge between quantum mechanics, general relativity, and information theory, offering profound insights into the fundamental structure of the cosmos. Simulation theory posits that what we perceive as reality might actually be an artificial construct, a highly advanced simulation created by a more technologically developed civilization. This idea has gained traction in both philosophical and scientific communities, particularly following the arguments presented by philosopher Nick Bostrom. According to Bostrom's simulation argument, one of three propositions must be true. Civilizations either go extinct before reaching a high level of technological maturity, advanced civilizations have no interest in creating simulations of their ancestors, or we are most likely living in a computer simulation. At the heart of simulation theory is the rapid advancement of computational power and digital technology. We are already seeing the creation of highly immersive virtual realities and complex simulations at a rudimentary level. If a civilization could advance far enough, it's conceivable that they could create simulations indistinguishable from actual reality. Such an advanced simulation would encompass not just environments, but the conscious experiences of individuals within it. The inhabitants of the simulation would then be oblivious to their artificial nature, perceiving their world as real. In terms of physical evidence or theoretical backing, simulation theory draws on the notion that fundamental aspects of our universe might be akin to digital information. For instance, the universe operates under a set of physical laws, which can be likened to the programmed rules of a computer simulation. Some even point to the discoveries in particle physics, such as the discrete nature of spacetime at the Planck scale, as potential indicators that our universe might be underpinned by a kind of computational framework. One intriguing angle comes from examining the behavior and limitations inherent in our universe. For example, quantum mechanics involves phenomena like superposition and entanglement, which can seem analogous to the processing shortcuts and optimizations developers might use in a simulation. Additionally, the holographic principle, which posits that the description of a volume of space can be encoded on a lower dimensional boundary, can also be seen as a parallel to how data is encoded and processed in sophisticated digital systems. Simulation theory not only reshapes our understanding of existence, but also opens up profound philosophical and ethical questions. If our universe is indeed a simulation, it brings into question the nature of consciousness, free will, and the ethics of creating simulated beings. It shifts the inquiry from exploring the physical cosmos to understanding the creator's intentions and the capabilities of the programmers shaping our perceived reality. Whether accepted as possible or dismissed as speculative fiction, simulation theory pushes us to consider the ultimate nature of existence and our place within it. The idea that the universe could be a simulation stirs both fascination and skepticism, prompting a range of arguments for and against. The evidence supporting the simulation theory often hinges on the intersection of technology, physics, and philosophical reasoning, while refutations typically focus on the conceptual and empirical challenges inherent in the theory. One line of supporting evidence comes from the increasing sophistication of our digital technologies. As virtual realities and simulations become more advanced, it is conceivable that a future civilization could create simulations indistinguishable from reality. Proponents argue that if such technology is possible, and if it becomes widespread, the sheer number of simulated realities could outnumber the base reality. Hence, the probability that we are living in one of many simulations increases. Another argument in favor comes from observations in physics that resemble attributes one might expect in a digital construct. For instance, the pixelated nature of space at the Planck scale suggests that the fabric of spacetime may not be continuous, but composed of discrete units, similar to pixels in a digital image. Additionally, some physicists have pointed out that the universe appears to follow specific mathematical laws and constants, akin to the coded rules in a simulation. The holographic principle, which suggests that all the information within a three-dimensional space can be encoded on a two-dimensional surface, also aligns curiously with how data storage and representation work in digital systems. However, several arguments refute the simulation theory. One major contention is the sheer computational power required to simulate an entire universe down to the quantum level. Simulating every particle interaction and the vast complexities of cosmological events would demand computational resources far beyond what we can currently imagine. Critics argue that while conceptually intriguing, the practical feasibility of such a simulation remains highly questionable. Additionally, there are philosophical objections. Some challenge the premise that a post-human civilization would necessarily want to create such simulations. They question the motivations and ethics behind simulating entire conscious beings, suggesting that advanced civilizations might have stringent moral guidelines preventing such creations. Empirically, we lack direct evidence to prove or disprove the simulation theory definitively. Our measurements and observations give no clear indication that the universe is an artificial construct. Some detractors argue that the simulation theory is unfalsifiable. It makes predictions that we currently cannot test or observe, thereby placing it outside the bounds of empirical science. In summary, While the simulation theory is an engaging hypothesis that aligns intriguingly with certain physical observations and technological trends, it remains speculative. The debate continues to stimulate rigorous discussions across multiple fields, from physics and philosophy to computer science and metaphysics, compelling us to ponder deeper questions about the nature of reality and our place within it. Virtual particles are an intriguing and fundamental concept in quantum field theory, a framework that combines classical field theory, special relativity, and quantum mechanics. Unlike real particles, virtual particles are transient, ephemeral entities that exist only for the briefest moments in the vacuum of space. They cannot be directly observed or detected, yet they play crucial roles in mediating forces and interactions between real particles, challenging our classical understanding of existence and reality. Virtual particles emerge from the inherent uncertainties of quantum mechanics, specifically Heisenberg's uncertainty principle, which allows for temporary violations of energy conservation. These fleeting entities pop in and out of existence within extremely short timescales, permitted by the uncertainty in energy and time. An example is the virtual photon that mediates the electromagnetic force between two charged particles. While the virtual photon itself cannot be detected, the force it mediates can be measured, showcasing its indirect but real influence on physical phenomena. The concept of virtual particles significantly challenges our classical notions of what it means to exist. Classical physics considers existence as an attribute of entities that persistently occupy a definite state and can be directly observed. However, virtual particles break this mold by existing only as transitory fluctuations within quantum fields. Their presence is inferred from the effects they produce, such as changes in particle trajectories or energy levels, rather than direct observation. One striking implication of virtual particles is their role in vacuum fluctuations, random variations in the energy of empty space due to the spontaneous creation and annihilation of virtual particle pairs. These fluctuations give rise to observable phenomena like the Casimir effect, where two uncharged parallel metal plates placed very close together in a vacuum experience an attractive force. This force arises from the restricted vacuum fluctuations between the plates compared to outside them, demonstrating the tangible impact of virtual particles on the physical world. Moreover, virtual particles are essential in understanding processes like Hawking radiation, where black holes can emit radiation due to particle-antiparticle pairs forming near the event horizon. One of these particles falls into the black hole, while the other escapes as Hawking radiation, contributing to the gradual evaporation of black holes over time. Virtual particles compel us to reconsider the boundaries between existence and non-existence, suggesting that the fabric of reality is far more complex and dynamic than our everyday experiences imply. They underscore a universe where even empty space is seething with activity and potential, governed by the probabilistic nature of quantum mechanics. This profound insight not only deepens our understanding of fundamental physics, but also invites us to embrace a more nuanced vision of existence itself. The concept of space-time introduced in Albert Einstein's theory of general relativity fundamentally challenges our traditional notions of a tangible, unchanging universe. Before Einstein, space and time were regarded as separate entities. Time flowed uniformly, and space was a static, three-dimensional stage where events occurred. This Newtonian view painted a picture of an absolute, unalterable universe where objects moved within a fixed backdrop. However, general relativity revolutionized this perspective by merging space and time into a dynamic, four-dimensional continuum called spacetime, where the fabric itself can be warped, stretched, and compressed by mass and energy. According to general relativity, massive objects like stars and planets cause a curvature or distortion in the spacetime around them. This curvature influences the paths that objects follow, which we experience as gravity. For example, the Earth orbits the Sun not because it is pulled by an invisible force, as Newton's laws would suggest, but because it follows a curved path within the warped spacetime created by the Sun's mass. This redefinition of gravity as a geometric property of spacetime rather than a force fundamentally alters our understanding of the universe. The implications of this are staggering and challenge our tangible, intuitive notions of reality. In a tangible Newtonian universe, space is rigid and unchanging, and time is a uniform, unceasing flow. But in the relativistic framework, space and time become malleable, dynamic entities. The presence of massive objects can stretch time, making it pass more slowly near strong gravitational fields, a phenomenon known as time dilation. This has been experimentally confirmed, for instance, by precise measurements showing that clocks aboard satellites in weaker gravitational fields tick faster than those on the Earth's surface. Furthermore, extreme gravitational effects such as those near black holes push these ideas even further. Near a black hole, space-time becomes so curved that it creates an event horizon, a boundary beyond which nothing can escape, not even light. The very structure of space-time becomes so warped that our everyday concepts of space and time break down entirely. One of the most profound predictions of general relativity is the existence of gravitational waves, ripples in the fabric of space-time caused by accelerating massive objects, like colliding black holes. The detection of these waves by observatories like LIGO has opened a new window into observing the universe, further revealing the dynamic, interconnected nature of space-time. This new understanding challenges the idea of a tangible, immutable universe. Instead, our reality is shaped by a fluid, ever-changing space-time fabric, where mass and energy dictate the geometry of the cosmos. General relativity forces us to reconsider the universe not as a static stage, but as a dynamic entity, where the interplay of space, time, and matter continuously shapes the very essence of reality itself. Black holes, with their extreme gravitational fields and enigmatic properties, present profound questions that challenge our understanding of reality, particularly through the lens of the information paradox. According to general relativity, black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape their event horizon. This leads to the classical depiction of black holes as cosmic traps where matter and information seemingly vanish forever, destined to become singularities, points of infinite density. However, this classical view comes into conflict with the principles of quantum mechanics, particularly the concept of information conservation. In quantum theory, information about the physical state of a system is preserved even if the system undergoes transformations. When matter falls into a black hole, it carries information about its physical state. The crux of the information paradox arises from the conundrum of what happens to this information once it crosses the event horizon. Stephen Hawking's groundbreaking work in the 1970s introduced the concept of Hawking radiation, where black holes can emit radiation due to quantum effects near the event horizon. Over time, this radiation causes the black hole to lose mass and eventually to evaporate completely. According to Hawking's original calculations, this radiation is thermal and seemingly random, carrying no specific information about the matter that fell into the black hole. This suggests that when a black hole evaporates, all information about its contents is irrevocably lost, violating the tenets of quantum mechanics and sparking the information paradox. This paradox forces us to question the consistency of our two most successful theoretical frameworks, general relativity and quantum mechanics. On one hand, general relativity describes the gravitational collapse into a black hole and its eventual evaporative processes. On the other hand, quantum mechanics insists on the preservation of information. Reconciling these conflicting viewpoints has led to intense theoretical investigations and numerous proposed solutions. One leading proposal is the idea of holography, where the information about the three-dimensional interior of a black hole is encoded on its two-dimensional boundary, known as the event horizon. This perspective aligns with the holographic principle, suggesting that the universe at large could operate under similar principles, where three-dimensional phenomena are encoded on a lower dimensional surface. Another approach involves the concept of black hole complementarity, which posits that information is both reflected at the event horizon and absorbed into the black hole, with no single observer able to perceive both processes simultaneously. This idea attempts to preserve unitarity in quantum mechanics without requiring a breakdown of general relativity. More recent theories include the hypothesis of firewalls, suggesting that an energetic barrier at the event horizon obliterates information, but this too remains controversial as it challenges the smooth classical structure of spacetime near the horizon. The information paradox illustrates the deep and unresolved tensions in our understanding of the universe's fundamental workings. It drives the quest for a unified theory of quantum gravity that can seamlessly integrate the principles of general relativity and quantum mechanics. In this endeavor, black holes act as natural laboratories, probing the very limits of our comprehension and continually reshaping our concepts of space, time, matter, and information. This ongoing exploration keeps us on the frontier of theoretical physics, unraveling mysteries that question the bedrock of reality itself. String theory offers a radical reimagining of the fundamental nature of reality. At its core, string theory posits that the most basic building blocks of the universe are not point-like particles as traditionally conceived in particle physics, but rather tiny, vibrating, one-dimensional strings. These strings can oscillate at different frequencies, and the various modes of vibration determine the properties of the particles, such as mass and charge, that we observe in the macroscopic world. This elegant framework holds the promise of unifying all fundamental forces and particles into a single, cohesive theory. One of the most compelling aspects of string theory is its potential to unify quantum mechanics and general relativity. Traditional quantum field theory, which describes the behavior of subatomic particles, and general relativity, which describes the gravitational force and the structure of spacetime, are currently incompatible at the most fundamental levels. String theory aims to bridge this gap by providing a quantum mechanical description of gravity. In this theory, the graviton, the hypothetical quantum particle that mediates the force of gravity, emerges naturally from the vibrations of closed strings, one of several types of strings theorized to exist. String theory introduces additional dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. While our everyday experience is confined to 4-dimensional spacetime, string theory typically requires the existence of 10 or even 11 dimensions for mathematical consistency. These extra dimensions are not directly observable because they are compactified or curled up at incredibly small scales, far beyond our current ability to detect. This concept vastly expands our understanding of the universe, suggesting that it is far richer and more complex than it appears at first glance. The idea of dualities further enriches string theory's conceptual landscape. Dualities are mathematical correspondences that reveal how seemingly different physical theories can be alternate descriptions of the same underlying reality. For instance, T-duality shows that large and small dimensions can be equivalent in certain respects, and S-duality connects weak and strong coupling regimes of the theory. These dualities imply that our understanding of space, time, and the interactions within them is even more interconnected than previously thought. One of the most intriguing features of string theory is the concept of the multiverse, which emerges from certain solutions to the equations governing the theory. These solutions suggest that our universe might be one of many possible universes, each with different physical properties and constants. The idea of a multiverse challenges our notions of uniqueness and fine-tuning, proposing that what we perceive as fundamental constants may vary across different regions of a vast multiverse. Despite its promise, string theory is not without its challenges and criticisms. One significant obstacle is the lack of experimental evidence. Many of the predictions of string theory occur at energy scales far beyond the reach of current particle accelerators, rendering them difficult, if not impossible, to test directly. This has led some critics to question whether string theory can be considered a scientific theory at all, as it currently lacks the falsifiability criterion that defines empirical science. In summary, string theory offers a profound and far-reaching vision of reality, one that seeks to unite the fundamental forces and particles into a single, elegant framework. By redefining the fundamental constituents of matter, introducing extra dimensions, and suggesting the existence of a multiverse, string theory radically expands our understanding of the universe and our place within it. Whether or not future experiments validate its predictions, string theory continues to be a rich source of insights and inspiration for physicists and cosmologists seeking to comprehend the deepest layers of reality. The concept of extra dimensions in string theory revolutionizes our understanding of the universe in profound ways. Traditionally, we have perceived the universe as existing in 3 spatial dimensions, with time as a 4th dimension. However, string theory, a pivotal framework in theoretical physics, posits that additional dimensions, potentially as many as 10 or 11, are required to unify the fundamental forces of nature. These extra dimensions are not observable in everyday life because they are thought to be compactified or curled up on themselves at incredibly small scales, far beyond the reach of our current experimental capabilities. The mind-bending idea is that what we perceive as a particle is actually a string vibrating at specific frequencies, and these vibrations occur not just in the familiar spatial dimensions, but in the additional hidden dimensions as well. The implications of extra dimensions are staggering. They offer potential solutions to some of the most perplexing problems in physics, such as the nature of black holes and the unification of gravity with quantum mechanics. In this framework, gravity might appear weak in our visible dimensions because it propagates through these additional hidden dimensions, diluting its apparent strength. This could also elucidate the enigmatic nature of dark matter and dark energy, possibly originating from interactions within these unseen dimensions. As we continue to explore string theory, our view of the universe might shift from a simple four-dimensional expanse to a complex, multi-dimensional tapestry where the laws of physics intertwine in ways we are only beginning to fathom. It opens a gateway to possibilities that redefine our cosmic landscape and stretches the boundaries of human imagination, aligning with the tantalizing mysteries that have always captivated us. Local reality is a foundational concept in classical physics and everyday experience, asserting that objects exist independently of observation and that their properties are definitively localized in space and time. In this intuitive framework, if you throw a ball, its trajectory and position are determined only by the forces acting on it, such as gravity and air resistance, and not by whether someone is observing it. This principle resonates deeply with our day-to-day interactions, grounding our sense of a consistent and predictable universe. However, the advent of quantum mechanics has dramatically challenged the notion of local reality. The theory suggests that particles do not have definite properties until they are measured, and their behavior can be influenced by distant events in ways that seem instantaneous, a phenomenon known as quantum entanglement. When two particles become entangled, the state of one particle is directly related to the state of the other, no matter the distance separating them. This non-local interdependence was famously encapsulated in the thought experiment known as Einstein's spooky action at a distance, highlighting a stark contrast to our classical perceptions. Local reality's clash with quantum mechanics was concretely demonstrated through John Bell's theorem, which showed that no local theory could reproduce all the predictions of quantum mechanics. Experiments have consistently supported the quantum view, implying that the universe at its most fundamental level defies our everyday understanding. These findings suggest a richer, more interconnected reality, where the classical notion of local, independent existence gives way to a more complicated and mysterious quantum world. This leap from the predictable to the probabilistic, and from the local to the non-local, presents one of the most profound shifts in our comprehension of the universe. It invites us to reconcile the seemingly disjointed realms of quantum mechanics and our macroscopic experiences, further deepening our quest to understand the true nature of reality. Experiments like those testing Bell's theorem essentially demolish the classical concept of local reality by empirically demonstrating that two entangled particles can exhibit correlations that are inexplicably connected, irrespective of distance. John Bell introduced his now famous theorem in the 1960s to put to test the idea that local hidden variables could explain the peculiarities of quantum phenomena. In simpler terms, he aimed to determine whether the strange behaviors predicted by quantum mechanics could be approximated by a yet-to-be-discovered classical theory that respects locality and determinism. Bell's theorem provides a mathematical framework that defines the limits of correlations predicted by any local realistic theory. By setting up an inequality, now known as Bell's inequality, he showed that if local realism held, the measured correlations between entangled particles would never exceed a certain threshold. Quantum mechanics, however, predicts that these correlations can and do surpass this limit under specific conditions. Experiments conducted over the past few decades have repeatedly validated the quantum mechanical predictions, most notably those by Alain Aspect in the 1980s, which meticulously closed several loopholes critics had previously pointed out. These experiments involved creating pairs of entangled particles, and measuring their properties in such a way that any signal or influence would be too slow to travel between the two particles, thus ensuring that any observed correlation could not be due to classical communication. The results consistently showed violations of Bell's inequality, meaning the entangled particles were influencing each other instantaneously, defying any concept of local causality. The implications of such results are staggering. They compel us to accept that particles do not have predefined states independent of their measurement, meaning that reality at a quantum level is profoundly interconnected in a non-local manner. Entanglement and the subsequent collapse of wave functions are inherently collective phenomena that transcend traditional bounds of space and time. Therefore, experiments validating Bell's theorem force us to reconsider our intuitive and classical understanding of the universe, nudging us toward a framework where the fabric of reality is fundamentally woven with threads of quantum interconnectedness. By doing so, they stretch the limits of our comprehension and pave the way for a richer, though more perplexing, understanding of the cosmos. Quantum entanglement is a phenomenon in which the quantum states of two or more particles become so deeply interconnected that the state of one particle instantaneously influences the state of the other, regardless of the distance separating them. This mysterious linkage was first discussed by Albert Einstein, Boris Podolsky, and Nathan Rosen in the 1930s in what became known as the EPR paradox. They presented this idea to highlight what they saw as the incompleteness of quantum mechanics, derisively calling the phenomenon spooky action at a distance. Entangled particles do not have individual independent states. Instead, their properties are intertwined in such a way that the measurement of one directly determines the state of the other. The conflict between quantum entanglement and local reality is stark. Local reality asserts that objects have predefined properties and that information cannot travel faster than the speed of light. Each object should be affected only by its immediate surroundings. Entanglement, on the other hand, suggests that two entangled particles behave as a singular system regardless of the spatial separation, violating the principle of locality. When one particle's state is measured, the state of the other particle instantly collapses to a corresponding value, as if the information about the measurement were transmitted faster than light, which fundamentally contradicts the relativistic constraint that nothing can exceed the speed of light. This discord was progressively unveiled through empirical tests of Bell's theorem, which showed that no theory rooted in local realism can replicate all the predictions of quantum mechanics. These experiments consistently reveal correlations between entangled particles exceeding the limits set by local theories, thereby validating the quantum predictions. For instance, if you measure the spin of one entangled electron, the spin of its partner electron, no matter how far away, will be found to be perfectly correlated, a result that defies any local explanation. Quantum entanglement thus necessitates a rethinking of our classical views, prompting us to explore a framework where the universe is non-local and interconnected in ways that elude straightforward intuition. It challenges the classical notion of separate, independent entities, and instead posits a reality where particles act in unison, linked by the invisible threads of quantum mechanics. This is not just a philosophical quandary, but a foundational aspect influencing quantum computing, cryptography, and our overarching comprehension of the fabric of reality itself. Non-locality in quantum mechanics refers to the phenomenon where particles that are entangled exhibit correlations that seem to defy the limitations imposed by the speed of light, which is the maximum speed for any signal or influence according to Einstein's theory of relativity. In simpler terms, non-locality suggests that the state of one particle can instantaneously affect the state of another distant particle, without any exchange of signals or information that would have to travel through space within the speed limit set by light. The concept is most famously illustrated by quantum entanglement. When two particles become entangled, their quantum states become interdependent. Measuring the state of one particle instantly determines the state of the other, no matter how far the particles have traveled from each other. This instantaneous connection persists even if the particles are separated by vast distances, potentially spanning the entire universe. This effect was starkly highlighted by the thought experiment proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen, the EPR paradox, which aimed to demonstrate what they believed was the incompleteness of quantum mechanics. The non-local nature of quantum mechanics was put to the test by John Bell through his theorem, which set the stage for numerous experiments, such as those by Alain Aspect and others. These empirical tests consistently showed that the correlations between entangled particles violate Bell's inequality, a benchmark that no local theory can surpass. This implies that no local hidden variable theory, in which particles have pre-existing properties determined by local information, can fully explain the observed quantum phenomena. Non-locality fundamentally challenges our classical intuitions about how the world operates. In a local realist view, objects are influenced only by their immediate surroundings, and any influence cannot propagate faster than light. Non-locality shatters this view by showing that entangled particles act as a single system, regardless of the spatial separation, thus suggesting that the universe at a fundamental level is more interconnected and holistic than previously imagined. This quantum non-locality does not allow for faster-than-light communication, preserving causality and adhering to the relativistic constraints in that respect. Rather, it reveals a deeply intertwined structure of reality that compels us to rethink our basic notions of space, time, and separateness. It serves as a cornerstone of quantum mechanics, influencing practical applications like quantum computing and quantum cryptography, while also fueling extensive philosophical debates about the true nature of reality. The counterintuitive essence of non-locality continues to intrigue and puzzle scientists, offering a glimpse into the enigmatic and beautifully complex quantum world. The ideas of quantum entanglement and non-locality provocatively redefine our traditional understanding of cause and effect in the universe. In classical mechanics, the notion of causality is straightforward. Events are ordered in a linear sequence where causes precede effects, and this chain of events is local, meaning influences propagate at or below the speed of light, respecting the boundaries set by relativity. Quantum mechanics, however, introduces a form of causality that is far less intuitive and more complex. When particles are entangled, their properties become correlated in such a way that the measurement of one particle immediately affects the state of the other, irrespective of the distance between them. This instantaneous connection poses a significant challenge to the classical idea that a cause must be local and must precede its effect by a measurable time interval. In the quantum realm, the cause-effect relationship appears to be non-local, connecting particles over any distance without a time lag that respects the speed of light constraint. This peculiar form of quantum causality doesn't allow for faster-than-light communication or time travel, which preserves overall causality and avoids paradoxes. However, it implies that events at the quantum level are interconnected in a holistic manner, where the act of measurement itself plays a crucial role in determining outcomes. Instead of one event causing another in a straightforward linear fashion, quantum events seem to be part of a globally correlated system where the traditional sequence of cause and effect can become blurred. These ideas force us to rethink many foundational aspects of physics and philosophy. The deterministic universe envisioned by classical mechanics, where every effect follows predictably from a cause, gives way to a probabilistic universe dictated by wave functions and observer interactions. This quantum perspective suggests that at the deepest levels of reality, the universe operates in an interconnected and non-local manner, defying the clean, compartmentalized views provided by classical theories. The challenge then becomes one of integrating this non-local quantum causality with our macroscopic classical world, a task that physicists and philosophers continue to grapple with. The implications extend beyond pure science into questions about the nature of free will, the role of an observer, and the ultimate structure of reality. As we delve deeper into these quantum mysteries, our understanding of cause and effect, once a cornerstone of scientific thought, undergoes a radical transformation, offering a richer but more complex picture of the cosmos that continues to inspire both awe and contemplation. One of the most significant real-world experiments that have tested the principles of local reality is Alain Aspect's series of experiments conducted in the early 1980s in France. These experiments were designed to test Bell's theorem, which states that no local hidden variable theories can reproduce all the predictions of quantum mechanics. Aspect and his team utilized pairs of entangled photons and measured their polarizations. Crucially, the experiments ensured that the settings for measuring these photons were changed rapidly during the experiment. Faster than any signal could travel between them, thereby addressing and eliminating potential locality loopholes. The results consistently violated Bell's inequality, providing strong evidence against local hidden variables and supporting the non-local nature of quantum entanglement. Another pivotal set of experiments were carried out by physicist John Clauser and his colleagues in the 1970s. Clauser's work built on Bell's theorem and set up an experiment using entangled photons to test for violations of Bell's inequality. Like aspects experiments, Clauser's results showed violations of Bell's inequality, aligning with quantum mechanical predictions and challenging local realism. These early experiments were foundational, building the momentum for further research in quantum entanglement. A more modern and comprehensive experiment can be highlighted in the work done by the research teams at Delft University of Technology in the Netherlands, published in 2015. This experiment, often referred to as a loophole-free Bell test, used entangled electrons in diamonds separated by over a kilometer. The researchers closed both the locality loophole and the detection loophole, ensuring that the measurement settings were chosen independently and that a high fraction of the entangled pairs were detected and measured. The results yet again showed strong violations of Bell's inequality, further confirming the non-local nature of quantum mechanics. These experiments and many like them provide robust empirical evidence that challenges the classical concept of local reality. They collectively demonstrate that the predictions of quantum mechanics hold true even under stringent and varied experimental conditions. This relentless validation of quantum weirdness not only refutes local hidden variables, but also opens up new avenues for practical quantum technologies, such as quantum computing and quantum cryptography. The profound implications of these findings continue to deepen our understanding of the fundamental nature of reality, blending the boundaries between the theoretical predictions and tangible scientific observation. Isaac Newton's and Albert Einstein's theories of gravity each revolutionized our understanding of this fundamental force, but they did so in profoundly different ways. In the 17th century, Isaac Newton introduced his theory of gravity, which was encapsulated in his law of universal gravitation. Newton posited that every mass exerts an attractive force on every other mass, a force that is proportional to the product of their masses and inversely proportional to the square of the distance separating them. This empirical formula could predict the motion of celestial bodies and objects on Earth with remarkable accuracy. Newton's theory framed gravity as a force acting instantaneously at a distance, establishing a deterministic view where the universe operates like a giant clockwork. The elegance and simplicity of Newton's equations dominated scientific thought for centuries, providing a robust framework for understanding planetary orbits, tides, and even the trajectories of projectiles. However, in the early 20th century, Albert Einstein transformed our understanding of gravity with his theory of general relativity. Unlike Newton, who described gravity as a force, Einstein conceptualized it as a curvature of spacetime itself. According to general relativity, massive objects cause spacetime to curve, and this curvature directs the motion of other objects. Imagine placing a heavy ball on a trampoline, creating a depression. Nearby objects will naturally roll towards the ball, not because a force pulls them, but because of the trampoline's shape. In a similar fashion, planets orbit the Sun not because they are pulled by an invisible force, but because the Sun's massive presence warps the spacetime around it, guiding the planets along curved paths. One of the most compelling evidences for general relativity was the observation of the bending of light from distant stars around the Sun during a solar eclipse in 1919. This phenomenon, known as gravitational lensing, was precisely predicted by Einstein's equations but entirely inexplicable by Newton's theory. Further confirmations came from the precise orbit of Mercury, the behavior of clocks in different gravitational potentials, and most recently, the detection of gravitational waves, ripples in the fabric of spacetime caused by accelerating massive objects, an extraordinary prediction of Einstein's theory validated by LIGO in 2015. Where Newton's theory excelled in its simplicity and predictive power within the relatively weak gravitational fields familiar to us, Einstein's general relativity provides a more comprehensive framework, particularly in extreme conditions such as near black holes or in the context of cosmology, where spacetime curvature and relativistic effects become pronounced. The transition from Newtonian gravity to Einsteinian curvature marks a profound paradigm shift from a force-centric to a geometry-centric view of the universe. Though Einstein's theory reduces to newtons in weak gravitational fields, its broader applicability and deeper insights continue to drive modern physics, guiding our explorations from the subatomic scales to the vast expanses of the cosmos. The significance of gravity not being a force in the context of general relativity is profound and far-reaching, reshaping our fundamental understanding of the universe. In Einstein's theory, gravity is re-envisioned not as a traditional force, but as a manifestation of the curvature of space-time caused by mass and energy. This conceptual leap offers several pivotal insights and advancements over the Newtonian framework. Firstly, by treating gravity as the curvature of space-time rather than a force, general relativity provides a more accurate description of how massive objects influence their surroundings. In this paradigm, objects follow curved paths or geodesics in the distorted space-time landscape. This allows general relativity to elegantly explain phenomena that Newton's laws could not. For instance, the precise perihelion shift of Mercury's orbit, which deviates slightly from the predictions made by Newtonian mechanics, can be accurately described through Einstein's curvature of space-time. Secondly, the reinterpretation also solves the issue of instantaneous action at a distance, a problematic feature of Newtonian gravity, which implies that changes in gravitational influence occur instantaneously, contradicting the finite speed of causality dictated by special relativity. In general relativity, changes in the gravitational field propagate at the speed of light through gravitational waves, ensuring consistency with the relativistic framework. This was spectacularly evidenced by the LIGO Observatory's detection of gravitational waves, ripples in spacetime, produced by colliding black holes billions of light-years away. Another significant implication of treating gravity as spacetime curvature is its alignment with and extension into modern cosmology. General relativity's equations, particularly the Einstein field equations, form the backbone of our understanding of the universe's large-scale structure and dynamics. They have led to remarkable predictions and observations, like the expanding universe, black holes as space-time singularities, and more recently, insights into the mysterious categories of dark matter and dark energy. Moreover, considering gravity as a geometric property of spacetime also paves the way for the unification of general relativity with other fundamental forces in physics, a long-standing goal in theoretical physics. While a complete theory of quantum gravity remains elusive, the geometric approach of general relativity has significantly influenced the development of various attempts at unification, such as string theory and loop quantum gravity. In practical terms, technological advancements and GPS systems also underpin the significance of general relativity. GPS satellites must account for the slight differences in time experienced due to the weaker gravity in orbit compared to the Earth's surface, an adjustment only accurately handled through the lens of general relativity. General relativity's perspective on gravity, not as a traditional force, but as the curvature of space-time transitions, our understanding from a Newtonian clockwork universe to a dynamic, interconnected fabric of spacetime. It elevates our grasp of the cosmos from descriptive to explanatory, providing a deeper, more coherent view of the underlying structure governing the movements and interactions of all celestial and terrestrial bodies. This shift not only enriches the realm of theoretical physics, but also enhances our practical capabilities and our philosophical reflections on the nature of reality itself. General relativity describes gravity as the curvature of spacetime by incorporating the revolutionary idea that mass and energy distort the fabric of spacetime itself, creating what we perceive as gravitational effects. This is fundamentally different from Newton's concept of gravity as a force acting at a distance. In Einstein's theory, an object's mass and energy influence the geometry of the surrounding spacetime, and this curvature directs the motion of other objects, effectively replacing the concept of a gravitational force with geometric properties of spacetime. Einstein's insight can be summarized through the Einstein field equations, which relate the presence of matter and energy, described by the energy-momentum tensor, to the geometric curvature of spacetime, described by the Einstein tensor. The simplest non-mathematical analogy often used to illustrate this is the rubber sheet model. Imagine a heavy ball placed on a stretched rubber sheet, the sheet will warp and curve around the ball. If you then roll a marble across the sheet, it will follow a curved path, not because a force is pulling it towards the ball, but because the sheet's curvature directs its motion. Similarly, in general relativity, planets orbit stars and objects fall towards the Earth because they are following the straightest possible paths, geodesics, in the curved spacetime created by massive objects. One of the most compelling ways this curvature manifests is in explaining phenomena such as the bending of light around massive objects, known as gravitational lensing. When light from a distant star passes near a massive object like a galaxy or a black hole, the spacetime curvature caused by the mass of the object causes the light to follow a curved path. This was empirically confirmed during the 1919 solar eclipse, when light from stars passing near the Sun was observed to bend, matching Einstein's predictions. Another critical evidence of spacetime curvature is the behavior of time in strong gravitational fields. According to general relativity, time runs slower in stronger gravitational fields, an effect known as gravitational time dilation. This has been confirmed by experiments involving highly precise atomic clocks, which run slightly faster at higher altitudes where the Earth's gravitational pull is weaker. Black holes, predicted by general relativity, are regions where spacetime curvature becomes extreme due to the presence of highly concentrated mass. Here, the warping effect is so pronounced that not even light can escape, delineating an event horizon beyond which traditional concepts of space and time cease to function as we know them. General relativity elegantly unifies gravity with the geometric fabric of spacetime, explaining gravitational phenomena not as the result of forces acting at a distance, but as consequences of curved spacetime geometry. This perspective fundamentally reshapes our understanding of the universe, from the orbits of planets to the expansion of the cosmos, providing a more comprehensive and interconnected framework of physical law. The curvature of spacetime, as described by Einstein's general theory of relativity, is robustly supported by a variety of experimental and observational evidence. Below are some key pieces of evidence that validate the concept of spacetime curvature. 1. Gravitational lensing. One of the most dramatic confirmations comes from the phenomenon of gravitational lensing, where light from distant stars or galaxies is bent as it passes near a massive object, such as a galaxy cluster. This bending effect was first confirmed during the 1919 solar eclipse by Sir Arthur Eddington, who observed that starlight passing near the Sun was indeed deflected by the precise amount predicted by Einstein's equations. Modern astronomical observations use gravitational lensing to detect otherwise invisible objects and to map the distribution of dark matter in the universe. 2. Perihelion precession of Mercury. The orbit of Mercury exhibits a small but measurable precession that couldn't be entirely accounted for by Newtonian mechanics. General relativity accurately explains this additional precession as a result of spacetime curvature caused by the Sun's mass. Albert Einstein's prediction concerning the exact amount of this precession was one of the early triumphs of his theory. 3. Gravitational time dilation. General relativity predicts that time runs slower in stronger gravitational fields. This has been confirmed through experiments such as the Haffel-Keating experiment in 1971, where atomic clocks flown on airplanes showed time dilation consistent with predictions. More precisely, the Global Positioning System, GPS, requires adjustments for gravitational time dilation to provide accurate positioning data. Without accounting for the curvature of spacetime, the time discrepancy would amount to a significant error in location accuracy. 4. Deflection of light by the Sun. Related to gravitational lensing, the deflection of light by the Sun has been observationally confirmed on numerous occasions beyond the 1919 expedition. Instruments and satellites continuously observe this deflection from different stars and galaxies, further validating Einstein's theory. 5. Gravitational redshift. This effect is predicted by general relativity and occurs when light or other electromagnetic radiation emitted from a source in a strong gravitational field is shifted to longer wavelengths, or redshifted. This was first experimentally confirmed by observing the redshift of light from the surface of white dwarf stars, and later with precision experiments, such as the Pound-Rebka experiment in 1959, conducted at Harvard University. 6. Binary pulsars and orbital decay. Observations of binary pulsar systems, such as the famous Hulse-Taylor binary pulsar discovered in 1974, show that the two neutron stars lose energy over time, causing them to spiral closer together. This energy loss is consistent with the emission of gravitational waves as predicted by general relativity. The rate of orbital decay measured corresponds precisely to predictions from Einstein's equations. 7. Detection of gravitational waves. Perhaps the most direct confirmation of space-time curvature and one of the most groundbreaking achievements in modern physics is the detection of gravitational waves. First directly observed by the LIGO, Laser Interferometer Gravitational Wave Observatory, collaboration in 2015, these ripples in space-time were generated by the collision of two black holes. This discovery not only validated a key prediction of general relativity, but also opened a new window into observing the universe. 8. Frame dragging. The Gravity Probe B mission, launched by NASA, confirmed the frame dragging effect, another prediction of general relativity. This phenomenon occurs when massive rotating objects, such as Earth, drag space-time around with them. The mission measured minuscule changes in the orientation of gyroscopes in space, consistent with Einstein's predictions. These multiple lines of evidence gathered over a century through various precise measurements and observations compellingly support the concept of space-time curvature at the heart of general relativity. They do not just verify the theory at specific scales or conditions, but reinforce its validity across a wide spectrum of scenarios, from everyday GPS accuracy to the cosmic ballet of colliding black holes, confirming Einstein's revolutionary vision of a dynamic, curved space-time. Gravitational waves provide compelling confirmation of several key aspects of general relativity, and their detection has marked one of the most significant milestones in modern physics. Gravitational waves are ripples in the fabric of space-time that travel at the speed of light, generated by some of the most cataclysmic events in the universe, such as the collision of black holes or neutron stars. These waves carry information about their origins and the nature of gravity itself, making them powerful tools for testing Einstein's theory. Here are the main ways in which gravitational waves confirm aspects of general relativity. 1. Direct detection validates predictions. The first direct detection of gravitational waves was accomplished by the Laser Interferometer Gravitational Wave Observatory, LIGO, in September 2015. The observed waves originated from a collision between two black holes around 1.3 billion light-years away. This detection confirmed a major prediction of general relativity, that accelerating massive objects would produce ripples in space-time. Prior to this, gravitational waves had been inferred indirectly, such as through the orbital decay of binary pulsars, but LIGO's detection provided direct observational evidence. 2. Waveform consistency with general relativity. The gravitational wave signals detected by LIGO are remarkably consistent with the waveforms predicted by general relativity for binary black hole mergers. These waveforms describe how the amplitude and frequency of the waves evolve over time as the black holes spiral toward each other, merge, and settle into a single, more massive black hole. The fact that the detected waveforms match theoretical predictions so precisely supports the accuracy of Einstein's equations, even in extreme conditions. 3. Speed of gravitational waves. General relativity predicts that gravitational waves travel at the speed of light. Observations have confirmed that the waves detected by LIGO and Virgo arrived simultaneously with signals detected by electromagnetic telescopes, such as gamma-ray bursts observed from neutron star mergers. This congruence in arrival times underlines the accuracy of the predicted speed of these waves. 4. Energy and momentum loss. General relativity predicts that systems losing energy through gravitational wave emission will show signs of orbital decay, similar to how the binary pulsar PSRB 1913+16, discovered by Hulse and Taylor, behaves. The precise measurements of this binary pulsar's orbital decay match predictions derived from general relativity, supporting the existence and energy-carrying properties of gravitational waves. The LIGO and Virgo detections offer real-time observations of this process. 5. Testing. Extreme gravitational fields. The detection of gravitational waves from events like black hole mergers allows scientists to probe the nature of gravity in extremely strong field regimes where deviations from general relativity might be expected if alternative theories of gravity were correct. So far, all observations have been consistent with the predictions of general relativity, reinforcing its validity even close to the very aspects of black holes. 6. Polarization. States of gravitational waves. General relativity predicts that gravitational waves have two polarization states, known as plus and cross polarizations. The observed patterns in interferometers like LIGO and Virgo align with these predictions, providing another layer of confirmation for the theory. Future detectors may detect additional modes suggested by alternative theories of gravity, but to date, the detections have exclusively matched the predictions of general relativity. 7. Multi-messenger. Astronomy. The simultaneous observation of gravitational waves and electromagnetic signals from neutron star mergers, such as the event GW 170817 observed in August 2017, not only confirmed the speed and polarization of gravitational waves, but also provided insights into other relativistic phenomena, like the production of heavy elements via the R process in kilonovae. This multi-messenger approach pushes the boundaries of how we understand astrophysical processes in a relativistic context. In summary, gravitational waves confirm multiple critical aspects of general relativity, from the fundamental nature of spacetime curvature and the propagation speed of gravitational interactions to the behavior of massive objects in extreme conditions. Every detection strengthens our confidence in general relativity, solidifying its role as the leading theory of gravitation and spacetime, and opens new windows into understanding the universe's most energetic and enigmatic events. Black holes play a crucial role in advancing our understanding of gravity and spacetime, serving both as theoretical laboratories and observational windows into the extreme predictions and behaviors of Einstein's general theory of relativity. Here are several key aspects of how black holes contribute to our comprehension of these fundamental concepts. 1. Testbeds for general relativity. Black holes are regions of spacetime where gravitational fields are so intense that they create conditions utterly unlike those found elsewhere in the universe. Their extreme environments provide unique opportunities to test the predictions of general relativity to the utmost limits. Observations of black holes, from their event horizons to the dynamics of matter around them, allow scientists to validate or challenge the theory in strong gravitational fields. 2. Gravitational waves and black hole mergers. The detection of gravitational waves originating from black hole mergers, as first observed by LIGO in 2015, provides direct evidence of spacetime curvature and offers insights into the nature of gravity in highly dynamic, high-energy regimes. These events validate Einstein's predictions regarding the propagation of gravitational waves and the behavior of spacetime during cosmic cataclysms. 3. Event horizon and singularity. Black holes have a boundary called the event horizon, beyond which nothing, not even light, can escape. Studying the event horizon allows researchers to explore the interface between observable and unobservable phenomena, pushing the boundaries of our understanding of what constitutes an event in spacetime. The singularity at a black hole's core, where density and curvature reach infinite values, challenges our current physics and suggests areas where a new quantum theory of gravity might be needed. 4. Black hole thermodynamics. The study of black holes has led to the development of black hole thermodynamics, which draws intriguing parallels between the laws of thermodynamics and the properties of black holes. The discovery that black holes can have entropy and temperature and can emit radiation, proposed by Stephen Hawking and known as Hawking radiation, bridges the gap between general relativity, quantum mechanics, and thermodynamics. This concept raises profound questions about the nature of information, entropy, and the ultimate fate of matter falling into black holes. 5. Galactic centers and growth. Supermassive black holes residing at the centers of most galaxies, including our Milky Way, play a significant role in galaxy formation and evolution. The dynamics of stars and gas near these supermassive black holes provide invaluable data for understanding the gravitational potential well and the influence exerted by these massive objects on galactic scales. Observing the motion of stars around the supermassive black hole in the Milky Way, Sagittarius A*, provides direct measurements of its mass and insights into relativistic effects in strong gravitational fields. 6. Information paradox and quantum gravity. Black holes present the information paradox, a puzzle concerning the fate of information that falls into a black hole. According to quantum mechanics, information cannot be destroyed, but general relativity suggests it could be lost beyond the event horizon. This paradox is a central issue in the quest for a theory of quantum gravity, pushing physicists to explore new ways of reconciling these foundational principles. Progress in this area could lead to a deeper understanding of the true nature of spacetime and gravity at quantum scales. 7. Observational evidence and imaging. The Event Horizon Telescope (EHT) collaboration, which produced the first image of a black hole's event horizon, M87*, in 2019, represents a monumental achievement in observational astrophysics. Capturing the shadow of a black hole and the surrounding accretion disk provides direct visual evidence of spacetime curvature and offers an unprecedented test for the predictions derived from general relativity. In summary, black holes are not just fascinating cosmic objects, but are also fundamental for understanding gravity and spacetime. They provide crucial tests for the limits of general relativity, offer insights into extreme gravitational and quantum phenomena, and illuminate the interconnected dynamics of the cosmos. By studying black holes, physicists hope to unravel deeper aspects of the universe's structure and the fundamental nature of reality, offering profound implications for both theoretical and observational physics. Quantum gravity is the theoretical framework that attempts to reconcile the principles of quantum mechanics, which governs the subatomic realm, with general relativity, which governs the cosmic scale and the fabric of spacetime. The goal is to formulate a unified theory that consistently describes gravity in a manner that is compatible with quantum phenomena. The quest for quantum gravity is a significant focus for physicists for several reasons. 1. Inconsistencies between quantum mechanics and general relativity. Quantum mechanics and general relativity are both incredibly successful in their respective domains. Quantum mechanics explains the behavior of particles and forces at the smallest scales, while general relativity describes the gravitational force and the structure of spacetime. However, the two theories are fundamentally incompatible when applied together. For example, general relativity breaks down at the Planck scale, where quantum effects of gravity become significant. A theory of quantum gravity would resolve these foundational inconsistencies, providing a coherent framework that encompasses both quantum mechanics and relativity. 2. Understanding the singularities. In general relativity, singularities, points where quantities like curvature become infinite, are predicted to occur inside black holes and at the Big Bang. At these points, the theory breaks down and can no longer provide useful physical descriptions. A quantum theory of gravity is expected to resolve these singularities by incorporating quantum effects, potentially offering insights into what happens inside black holes and what occurred at the very beginning of the universe. 3. Unifying the forces. One of the great goals of theoretical physics is the unification of all fundamental forces into a single framework, often referred to as a theory of everything. Currently, three fundamental forces, electromagnetic, weak nuclear, and strong nuclear forces, are described by quantum field theory, while gravity is described by general relativity. Quantum gravity aims to incorporate gravity into a quantum framework, which would be a major step toward a unified theory. 4. Insights into spacetime structure. Quantum gravity could provide new insights into the very nature of spacetime. Concepts like spacetime quantization, where spacetime may have a discrete structure at the smallest scales, challenge our current continuum-based understanding. These ideas could lead to a deeper understanding of space, time, and causality, profoundly influencing our comprehension of the universe's fabric. 5. Technological advancements. While the primary motivation is theoretical, the development of quantum gravity could have unforeseen technological implications, similar to how quantum mechanics led to the development of technologies such as transistors, lasers, and MRI machines. The unification and deeper understanding of fundamental forces and particles might spur innovations that could transform various technologies. Several leading approaches to quantum gravity have been developed, each attempting to tackle the problem from different angles. String theory proposes that the fundamental constituents of reality are not point particles but one-dimensional strings whose vibrations correspond to different particles. String theory is a candidate for unifying all forces, including gravity, within its framework. Loop quantum gravity. This approach seeks to quantize space-time directly, suggesting that space and time have a discrete granular structure. It avoids the need for extra dimensions and focuses directly on the geometric properties of space-time. Causal dynamical triangulations, CDT. This approach models space-time as a collection of simple building blocks, seeking to provide a quantum description of gravity by summing over different possible geometries. Emergent gravity and holography. Some theories suggest gravity might emerge from more fundamental quantum entanglements, drawing connections between gravity and quantum information theory. The holographic principle, inspired by string theory, posits that a higher dimensional universe can be described by a lower dimensional boundary theory. The search for quantum gravity is a rigorous and demanding endeavor that bridges multiple disciplines in physics, from particle physics to cosmology, and even into the realms of mathematics and philosophy. The discovery of a successful theory of quantum gravity would not only solve a long-standing puzzle, but also potentially revolutionize our understanding of the universe, opening new frontiers in both theoretical and experimental physics. It represents the frontier of our quest for a deeper, more unified understanding of the natural world. Current theories of quantum gravity explore various innovative approaches to unify gravity with quantum mechanics, addressing the foundational conflicts and aiming to formulate a coherent framework that encompasses both realms. Each theory offers unique insights and potential solutions to this grand challenge in physics. Here are some of the leading efforts. 1. String theory. String theory posits that the fundamental constituents of reality are not point particles but one-dimensional strings vibrating at specific frequencies. Different vibrational modes of these strings correspond to different particles, including the graviton, which is the hypothetical quantum particle that mediates the force of gravity. String theory inherently includes gravity and aims to unify all the fundamental forces within its framework. It requires additional dimensions, typically 10 or 11, to be mathematically consistent. These extra dimensions are thought to be compactified or curled up at scales too small to be observed. String theory provides a framework in which quantum field theory and general relativity can coexist, offering potential pathways to a unified description of nature. 2. Loop quantum gravity, LQG. Loop quantum gravity attempts to directly quantize spacetime itself, proposing that spacetime is composed of discrete, quantized units, much like matter is composed of atoms. This approach uses the mathematics of spin networks and spin foams to describe the quantum states of spacetime. In LQG, space is not continuous but has a granular structure at the Planck scale. LQG avoids the need for higher dimensions and focuses on the geometric properties of spacetime, predicting that singularities, such as those inside black holes or at the Big Bang, are resolved into finite structures. 3. Causal dynamical triangulations, CDT. Causal dynamical triangulations is a non-perturbative approach to quantum gravity that models spacetime as consisting of discrete building blocks called simplices. CDT aims to sum over different possible geometries of spacetime, emphasizing the importance of causality in the quantum description. By constructing spacetime from these simplices in a way that respects causal relationships, CDT researchers hope to recover a smooth, classical spacetime at large scales while preserving quantum properties at the microscopic level. 4. Holographic principle and ADS-CFT correspondence. The holographic principle suggests that the entire volume of a region of space can be described by information encoded on its boundary. This principle is exemplified by the anti-de Sitter conformal field theory ADS-CFT correspondence proposed by Juan Maldacena. The ADS-CFT correspondence posits a relationship between a gravitational theory in a higher dimensional ADS space and a conformal field theory, CFT, on its lower dimensional boundary. This duality provides a powerful tool for understanding quantum gravity, as complex problems in a gravitational theory can be translated into more tractable problems in a quantum field theory. 5. Emergent gravity and entropic gravity. Some approaches suggest that gravity might not be a fundamental force, but an emergent phenomenon arising from the entropic and informational properties of spacetime. The idea, pioneered by Eric Verlinde and others, posits that gravity emerges from changes in entropy associated with the distribution of quantum information. In this view, spacetime and gravitational dynamics could arise naturally from underlying quantum entanglement. 6. Asymptotic safety. The asymptotic safety approach proposed by Steven Weinberg suggests that gravity can be quantized in a way that remains finite and predictive at all energy scales. The core idea is that there exists a non-trivial ultraviolet fixed point where the renormalization group flow of gravitational couplings becomes stable, preventing divergences. Each of these theories approaches the problem of unifying gravity with quantum mechanics from different angles, reflecting the multifaceted nature of the challenge. String theory provides a broad framework incorporating all fundamental forces, while loop quantum gravity and CDT focus on the quantization of spacetime itself. The holographic principle offers deep insights into the relationship between gravity and quantum field theories, and emergent and entropic gravity suggests fundamentally new ways of thinking about the nature of gravity. While a definitive, experimentally verified theory of quantum gravity remains elusive, these approaches collectively push the boundaries of our understanding, inspire new lines of inquiry, and guide experimental efforts. Successful unification could transform our comprehension of the universe, revealing new truths about the fabric of reality and unlocking new technological possibilities. Physicists employ a combination of observational data and experimental techniques to test theories about the fabric of spacetime. One prominent method is the use of gravitational wave detectors, like the Laser Interferometer Gravitational Wave Observatory, or LIGO. In September 2015, LIGO made history by directly detecting gravitational waves, ripples in spacetime caused by the collision of two black holes. This groundbreaking discovery not only confirmed a prediction made by Albert Einstein's general theory of relativity a century ago, but also opened up a new way of observing the cosmos, enabling scientists to gather evidence about the properties and behavior of spacetime under extreme conditions. Additionally, physicists test these theories by studying the cosmic microwave background radiation, the relic radiation left over from the Big Bang. By meticulously analyzing the minute fluctuations in this ancient light, scientists can glean insights into the structure and evolution of the universe, testing predictions of both general relativity and theories that attempt to unify it with quantum mechanics. For instance, experiments like those conducted by the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided detailed maps of the cosmic microwave background, allowing researchers to probe the universe's infancy with incredible precision. These experiments collectively help us understand the very fabric of spacetime, from the vast stretches of intergalactic voids to the high-energy events like the merging of neutron stars. The notion of wormholes and spacetime bridges profoundly challenges our understanding of space and time, surfacing speculative yet intriguing possibilities that stretch the boundaries of current physics. Wormholes, also referred to as Einstein-Rosen bridges, are theoretical passages through spacetime that could create shortcuts for long journeys across the universe. According to the equations of general relativity, a wormhole could connect two distant points in spacetime, potentially allowing travel between them far quicker than the distance between them in normal space would allow. However, these concepts raise significant theoretical and practical challenges, as the conditions required to sustain a traversable wormhole might demand forms of matter with negative energy, something not known to exist in the necessary quantities. Furthermore, Wormholes introduce profound implications for causality and the nature of our universe. If one end of a wormhole were to be accelerated to relativistic speeds and then brought back, time dilation could allow for time travel to the past or future, thereby challenging our very understanding of temporal order. While these theoretical constructs are fascinating, they remain firmly in the realm of mathematics and imagination, as no empirical evidence currently supports their existence. This speculative nature forces physicists to constantly reevaluate the foundational concepts of space, time, and the limits of our physical laws, illustrating how much we have yet to understand about the universe's ultimate structure and the potential hidden dimensions within it. The event horizon of a black hole is an integral facet of our understanding of gravity and spacetime, pushing the limits of theoretical physics. The event horizon represents the boundary beyond which nothing, not even light, can escape the gravitational pull of the black hole. This threshold offers a unique natural laboratory for probing the extremes of gravity, encapsulating conditions where the effects of general relativity become starkly evident. Understanding the event horizon helps physicists explore the nature of singularities, where the gravitational forces are so intense that they warp spacetime to an infinite degree, posing significant challenges to our comprehension of physical laws. One of the most intriguing implications of the event horizon is encapsulated in the enigmatic information paradox. According to classical general relativity, information that crosses the event horizon is lost to the outside universe. However, quantum mechanics dictates that information cannot be destroyed, suggesting a standoff between two foundational theories. The investigation into this paradox has given rise to groundbreaking concepts like Hawking radiation, theorized by physicist Stephen Hawking in 1974. Hawking proposed that black holes could emit radiation due to quantum effects near the event horizon, leading to the gradual evaporation of the black hole and hinting at possible mechanisms by which information might be preserved. These studies are paving the way for a unified theory of quantum gravity, inching us closer to understanding the deepest mysteries of the cosmos. Dark matter and dark energy are two enigmatic components of the universe that significantly influence our understanding of gravity and spacetime, challenging and expanding traditional frameworks. Dark matter, which constitutes approximately 27% of the universe, does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. It plays a crucial role in the formation and structure of galaxies, acting as the unseen scaffolding that holds cosmic structures together. Observations of galactic rotation curves, where the outer regions of galaxies rotate at unexpected speeds, and gravitational lensing, where light from distant objects is bent by unseen mass, provide compelling evidence of dark matter's gravitational influences. These anomalies cannot be explained by ordinary matter alone, pushing scientists to reconsider the nature of gravity on galactic and intergalactic scales. On the other hand, dark energy, estimated to make up a staggering 68% of the universe, is hypothesized to be responsible for the accelerated expansion of the cosmos. Discovered through observations of distant supernovae in the late 20th century, dark energy acts as a repulsive force counteracting gravity on cosmological scales. Its presence necessitates a modification of Einstein's equations of general relativity to include a cosmological constant, or invoke new theoretical models such as quintessence, dynamic fields that influence the expansion rate. The interplay of dark matter and dark energy reshapes our understanding of spacetime, hinting at a deeper, more complex cosmic fabric that we have just begun to unravel. These mysterious components invite a reimagination of gravity, potentially leading us towards new, uncharted territories in theoretical physics. The expansion of the universe is fundamentally intertwined with the fabric of spacetime and offers profound insights into its nature and dynamics. This expansive phenomenon is described by the general theory of relativity, where Albert Einstein's field equations depict gravity as the warping of spacetime by mass and energy. In this framework, the universe itself, described by solutions to these equations, including the Friedmann-Lemaitre-Robertson-Walker metric, evolves over time. During the early 20th century, astronomer Edwin Hubble provided observational evidence that the universe is expanding by discovering that distant galaxies are receding from us, with their light increasingly redshifted. This phenomenon suggests that the fabric of spacetime is stretching, causing galaxies to move away from one another. As space-time expands, it carries galaxies along for the ride, akin to dots on a balloon's surface moving apart as the balloon inflates. This dynamic nature of space-time leads to remarkable implications about the universe's history and future. The realization that the universe is not static but expanding laid the groundwork for the Big Bang theory, which posits that the universe originated from an extremely hot, dense state approximately 13.8 billion years ago. Moreover, recent observations indicate that this expansion is accelerating, driven by the elusive force known as dark energy. This accelerated expansion influences cosmological models and our understanding of the ultimate fate of the universe, whether it will continue to expand indefinitely, succumb to a big freeze, or experience a dramatic big rip. Exploring the interplay between the universe's expansion and the fabric of spacetime remains at the frontier of cosmology, continually reshaping our comprehension of the cosmos. Physicists employ a variety of sophisticated methods to study the effects of gravity in extreme conditions, such as those found near black holes, to test and refine their understanding of the fundamental laws of physics. One primary approach is the use of high-resolution astronomical observations, made possible by advanced telescopes and observatories. Instruments like the Event Horizon Telescope, EHT, have produced groundbreaking images of black holes, such as the historic image of the supermassive black hole in the galaxy M87 captured in 2019. By observing the event horizon, the boundary beyond which nothing can escape, a wealth of data is gathered about the intense gravitational fields and the behavior of matter and light in extreme conditions. Simulations and theoretical models also play an essential role in this exploration. Physicists use supercomputers to run simulations based on the equations of general relativity to predict how matter and radiation should behave in the vicinity of black holes. These models help interpret observational data and predict phenomena such as gravitational waves. The detection of gravitational waves by observatories like LIGO and Virgo, first confirmed in 2015 with the observation of a binary black hole merger, has provided direct evidence of the ripples in spacetime caused by massive cosmic events. These detections allow scientists to study the dynamics of spacetime under the most extreme gravitational conditions, offering invaluable insights into the properties of black holes and testing the limits of our understanding of gravity. Additionally, studying the behavior of matter in accretion disks around black holes, where gas, dust, and other debris spiral inward and heat up to extreme temperatures, provides observable signatures that help test theoretical predictions. X-ray observatories such as NASA's Chandra X-ray Observatory and ESA's XMM Newton detect high-energy radiation emitted from these hot accretion disks, revealing details about the extreme gravitational and magnetic environments present. Through these combined observational, theoretical, and computational efforts, physicists continue to uncover the mysteries of gravity in the universe's most extreme contexts, pushing the boundaries of modern science. The influence of gravity on time, as vividly depicted in the movie Interstellar, is grounded in the principles of Einstein's general theory of relativity. This phenomenon, known as gravitational time dilation, occurs because massive objects like black holes warp the fabric of spacetime. According to relativity, the stronger the gravitational field, the slower time passes near the massive object compared to regions with weaker gravitational fields. This effect is not just theoretical, but has been confirmed by various experiments and observations. In Interstellar, one striking illustration of gravitational time dilation occurs when the protagonists visit a planet orbiting close to a supermassive black hole named Gargantua. The immense gravity of the black hole causes time on the planet to pass much more slowly compared to Earth. For every hour spent on the planet, several years pass on Earth. This dramatic portrayal is consistent with relativity's predictions. Near a black hole, the space-time curvature is so intense that it stretches time to an extraordinary degree. In our daily lives, gravitational time dilation is negligible but still detectable. For instance, precision timekeeping devices like atomic clocks placed at different altitudes on Earth, one at sea level and one on a mountain, show slight differences in elapsed time due to the variance in gravitational strength. This effect has even been accounted for in the Global Positioning System, GPS satellites, which must correct for time dilation to provide accurate positioning data. The concept that gravity affects time revolutionizes our understanding of the universe. blending the dimensions of space and time into a single four-dimensional continuum. It underscores how gravity not only influences the motion of objects, but also the very fabric of reality itself, weaving an intricate tapestry where mass, space, and time are inextricably linked. As scientists continue to study these phenomena in extreme environments such as near black holes, they deepen our comprehension of the fundamental forces shaping the cosmos. Gravitational lenses are fascinating astronomical phenomena resulting from the warping of space-time by massive objects, such as galaxies or clusters of galaxies. According to Einstein's general theory of relativity, light from a distant object can be bent by the gravitational field of an intervening massive object, acting much like a lens in an optical instrument. This effect, known as gravitational lensing, can magnify, distort, and multiply the images of background objects, enabling astronomers to observe galaxies and cosmic structures far beyond the reach of traditional telescopes. Gravitational lensing occurs in two primary forms: strong lensing and weak lensing. In strong lensing, the alignment between the source, lens, and observer is precise, producing highly visible distortions such as arcs, rings, known as Einstein rings, and multiple images of the same astronomical object. These striking visual effects occur when the light from a distant background galaxy or quasar passes near a massive foreground galaxy cluster, allowing astronomers to study these far-flung objects in much greater detail. Strong lensing has led to the discovery of some of the universe's most distant galaxies, by providing a natural magnification that makes them detectable with current observational technologies. Weak lensing, on the other hand, involves more subtle distortions of background galaxies caused by the gravitational influence of less massive foreground structures. While individual distortions are minor, statistical analysis of these effects in large sky surveys reveals the distribution and characteristics of dark matter in the universe. By mapping these weak lensing effects, astronomers gain insights into the large-scale structure of the cosmos and the mysterious nature of dark matter, which does not emit, absorb, or reflect light, but exerts a significant gravitational influence. Gravitational lensing thus serves as a powerful tool in cosmic exploration. It extends our observational reach, allows the study of extremely distant and faint objects with increased precision, and provides critical information on the distribution of mass, including dark matter, in the universe. Employing gravitational lenses, astronomers continue to unravel the complexities of cosmic evolution, the formation of structures in the universe, and the underlying forces that govern these processes. The discovery of the constant speed of light, as encapsulated in Albert Einstein's theory of special relativity in 1905, revolutionized physics by fundamentally altering our understanding of space, time, and the nature of the universe. Before this breakthrough, the prevailing physics was grounded in Newtonian mechanics, which assumed that time and space were absolute and independent entities. Einstein's revelation that the speed of light in a vacuum is always the same, approximately 186,282 miles per second, regardless of the observer's state of motion, upended these classical notions and led to a new framework for comprehending the physical world. One of the most profound consequences of the constant speed of light is the concept of space-time. Special relativity demonstrates that space and time are not separate, but rather interwoven into a four-dimensional continuum. This fusion means that the measurements of space and time are relative to the observer's velocity. Time dilation and length contraction are direct results of this relationship, indicating that time passes more slowly and lengths contract as an object approaches the speed of light. These effects, while imperceptible at everyday speeds, become significant at velocities close to the speed of light, with critical implications for high-speed travel and astrophysical phenomena. Einstein's insights also led to the famous equation E equals sin mc squared, revealing the equivalence of mass and energy. This equation indicates that mass can be converted into energy and vice versa, a principle that underlies the workings of nuclear reactions and has profound implications for both theoretical and applied physics. For example, it explains the immense energy released in nuclear fission and fusion processes, as seen in both astrophysical events such as supernovae and technological applications like nuclear power. Moreover, the constancy of the speed of light became a cornerstone for Einstein's later development of general relativity, which extended these concepts to include gravity as a warping of space-time by mass and energy. This new paradigm provided an accurate description of gravitation, predicting phenomena like the bending of light by gravity, gravitational lensing, time dilation near massive objects, and the expansion of the universe. The discovery of the constant speed of light not only rectified inconsistencies in classical physics, but also paved the way for a deeper and more comprehensive understanding of the cosmos. It transformed our view of fundamental concepts and continues to guide contemporary research in both theoretical and experimental physics, shaping the quest to uncover the ultimate nature of reality. The constancy of the speed of light has been confirmed through a variety of pivotal experiments, reinforcing its foundational role in modern physics. One of the earliest and most famous of these experiments was conducted by Albert A. Michelson and Edward W. Morley in 1887, known as the Michelson-Morley experiment. This experiment aimed to detect the relative motion of matter through the hypothesized luminiferous ether, a medium then thought to permeate space and carry light waves. Using an interferometer to measure the speed of light in perpendicular directions, Michelson and Morley found no variation, suggesting that light speed is invariant and not influenced by the motion through any such medium. This null result was a crucial piece of evidence leading to the abandonment of the ether concept and the subsequent development of special relativity. Another important confirmation came from time dilation experiments involving highly accurate atomic clocks. One notable example is the Haffler-Keating experiment in 1971, where cesium atomic clocks were flown around the world on commercial airplanes and then compared to stationary clocks. The results matched the predictions of special relativity, illustrating that time dilates according to the relative motion of the observers, which indirectly corroborates the constancy of the speed of light. Modern experiments continue to validate the invariance of light speed. The synchronization of atomic clocks in the Global Positioning System, GPS, relies on the constant speed of light to provide accurate positioning data. If the speed of light varied by direction or observer's motion, GPS calculations would quickly become inaccurate. Laboratory tests such as those using high-energy particle accelerators have tested the principles of special relativity with extraordinary precision. These experiments involve accelerating particles to speeds close to that of light and observing their behavior. For example, the relativistic energy and momentum relationships derived from special relativity have been confirmed with great accuracy, reinforcing the idea that the speed of light remains constant regardless of the observer's frame of reference. Cumulative evidence from these diverse experiments across both classical and modern contexts provides robust validation for the constancy of the speed of light, underpinning our most successful physical theories and technological applications. The constancy of the speed of light fundamentally alters our understanding of spacetime, merging what were once thought to be distinct entities into a unified four-dimensional continuum. This revolutionary concept, introduced by Albert Einstein's theory of special relativity, reveals that space and time are not absolute but interdependent and relative to the observer's motion. The speed of light serves as a cosmic speed limit, and its invariance influences several key aspects of spacetime. Firstly, the constancy of the speed of light leads directly to time dilation and length contraction. As an object's velocity approaches the speed of light, time experienced by that object slows down relative to a stationary observer, and its length contracts along the direction of motion. These effects are not mere theoretical constructs, but have been experimentally verified and have practical implications, such as the need to account for time dilation in the synchronization of GPS satellites with Earth-based systems. Secondly, the speed of light underpins the concept of simultaneity. According to special relativity, events that occur simultaneously for one observer may not be simultaneous for another moving at a different velocity. This relativity of simultaneity arises because the speed of light remains constant for all observers, regardless of their relative motion. Consequently, measurements of time and space become relative, depending on the observer's frame of reference. In general relativity, the speed of light also plays a crucial role in describing how gravity influences spacetime. Massive objects, such as stars or black holes, curve the fabric of spacetime, and this curvature directs the motion of objects and light. The The bending of light around massive objects, known as gravitational lensing, is a direct consequence of the curvature of space-time. This effect has been observed and utilized in astronomical observations to study distant galaxies and map the distribution of dark matter in the universe. Moreover, Einstein's famous equation, E equals mc², where CE represents the speed of light, reveals the equivalence of mass and energy, highlighting the profound interconnectedness of matter and energy within the structure of space-time. This equivalence has been instrumental in understanding nuclear reactions and the energy output of stars. Overall, the speed of light is central to the modern understanding of the cosmos. It transforms the way we perceive distances, durations, and interactions across the universe. The intertwined nature of space and time, dictated by the speed of light, encourages a deeper exploration of the cosmos, pushing the boundaries of knowledge and revealing the intricate dance of the universal fabric. The speed of light imposes significant constraints on both travel and communication across the universe due to its role as a cosmic speed limit. According to Einstein's theory of relativity, the speed of light in a vacuum, approximately 186,282 miles per second, is the maximum speed at which information or matter can travel. This limitation profoundly affects our ability to explore and understand the vast expanses of space. For space travel, reaching even a fraction of the speed of light requires technology and energy resources far beyond our current capabilities. As an object approaches the speed of light, its mass effectively increases, necessitating exponentially more energy to continue accelerating. Our most advanced spacecraft travel at a minuscule fraction of the speed of light, meaning interstellar travel to even the nearest stars could take thousands to millions of years with current technology. This distance renders human space exploration limited to our own solar system for the foreseeable future. Regarding communication, the finite speed of light results in time lags that significantly affect operations over astronomical distances. For example, light from the sun takes about 8 minutes to reach Earth, meaning we see the sun as it was 8 minutes ago. Communication with spacecraft on Mars, depending on the planet's relative positions in their orbits, experiences delays ranging from several minutes to over 20 minutes. For missions further afield, such as the Voyager probes now in interstellar space, these delays extend to many hours. Crucially, these time delays complicate real-time communication and control of distant robotic missions and potential human crews on other planets. They pose strategic and operational challenges for scientific data transmission and remote control of extraterrestrial rovers, demanding advanced autonomous systems and pre-programmed instructions to cope with communication lags. On a larger cosmological scale, the speed of light shapes our perception of the universe. Distant objects we observe through telescopes are seen as they were millions or even billions of years ago, given the time it takes light to travel from these objects to Earth. This look-back time means that we are observing the history of the universe, not its current state, offering a window into the past, but complicating our understanding of its present dynamics. In sum, the speed of light imposes profound limitations on our ability to travel and communicate over cosmic distances, influencing the scope of our exploration, the timing of our interactions, and our perception of the universe. These constraints necessitate innovative approaches and long-term planning to advance our quest for knowledge and exploration of the cosmos. The concept of faster-than-light (FTL) travel has captivated human imagination for decades, but according to current physics, it presents numerous challenges and seemingly insurmountable barriers. At the core of these challenges is the cornerstone of Einstein's theory of relativity, which asserts that the speed of light in a vacuum is an absolute maximum speed, with significant implications for energy requirements, causality, and the very fabric of space-time. Firstly, the energy requirements for accelerating an object to the speed of light are prohibitive. As an object's velocity approaches the speed of light, its relativistic mass increases asymptotically, requiring exponentially greater energy input. Moreover, FTL travel introduces paradoxical implications for causality, our understanding of cause and effect. According to relativity, surpassing the speed of light could lead to situations where an effect precedes its cause, violating the principle of causality and creating potential paradoxes such as the famous grandfather paradox. This would undermine the logical consistency of physical laws and our understanding of time. There are also theoretical constructs like wormholes and warp drives that are often speculated as mechanisms for FTL travel. Wormholes, or Einstein-Rosen bridges, theoretically connect distant points in spacetime, acting as shortcuts. However, maintaining a stable wormhole would likely require exotic matter with negative energy density, a form of matter not known to exist in quantities necessary for this purpose. Similarly, a warp drive, such as the hypothetical Alcubierre drive, proposes a mechanism that contracts spacetime in front of a vessel and expands it behind, effectively allowing it to travel faster than light relative to distant observers. Yet this too demands negative energy and an unknown method to generate and manage it on a cosmic scale. Despite these daunting theoretical challenges, considering FTL travel expands our understanding of physics boundaries and encourages exploration into uncharted territories of theoretical physics. For instance, the study of quantum entanglement hints at instantaneous correlations between distant particles, raising questions about the underlying structure of spacetime and information transfer. Though not equivalent to FTL travel, these phenomena compel physicists to reconsider and refine our understanding of nature. In conclusion, while FTL travel remains within the realm of science fiction given current physical laws, exploring its theoretical underpinnings fosters scientific inquiry and enhances our grasp of the universe's fundamental principles. The profound implications and challenges associated with FTL travel illuminate the intricate and delicate fabric of spacetime that governs our reality, suggesting that to transcend these limits, humanity would need an unprecedented breakthrough in the understanding of physics. Time dilation and length contraction are two of the most intriguing and counterintuitive phenomena that arise from Einstein's theory of special relativity, fundamentally altering our classical understanding of space and time. These effects emerge directly from the postulate that the speed of light is constant for all observers, regardless of their relative motion. This constancy leads to a dramatic rethinking of how time and space operate, particularly at velocities approaching the speed of light. Time dilation refers to the effect where time appears to pass more slowly for an object moving relative to an observer at rest. This means that a clock moving at high speeds ticks more slowly compared to one at rest. This phenomenon has been experimentally verified through high-precision atomic clocks flown on aircraft or satellites, which show measurable differences in elapsed time compared to clocks on the ground. Length contraction, on the other hand, is the phenomenon where the length of an object moving relative to an observer's frame of reference appears contracted along the direction of its motion. Essentially, a spaceship traveling at relativistic speeds would appear shorter along its direction of motion to a stationary observer. Together, these phenomena underscore the fluid nature of spacetime in the relativistic framework. They break the Newtonian assumptions of absolute time and space, revealing a reality where measurements of length and duration are relative and depend on the observer's state of motion. These effects become pronounced only at velocities significant fractions of the speed of light, which is why they are not noticeable in everyday experiences. The implications of time dilation and length contraction extend into various fields, including astrophysics and engineering. For example, they are crucial for the synchronization of satellite-based navigation systems like GPS, which must account for both gravitational time dilation, a general relativity effect, and velocity-induced time dilation to provide accurate positioning data. Additionally, particle accelerators routinely observe these relativistic effects as particles approach light speed, requiring adjustments to maintain synchronization and functionality. Overall, time dilation and length contraction highlight the inherent flexibility of space and time and continue to challenge our perceptions, offering a deeper understanding of the universe's fundamental nature. The concept of causality, which asserts that cause precedes effect, is fundamentally tied to the speed of light within the framework of relativity. According to Einstein's theories, the speed of light in a vacuum is the ultimate speed limit for the transmission of information and the propagation of physical effects. This principle ensures that causal relationships are maintained consistently across different reference frames. In special relativity, the light cone structure demarcates the causal terrain of events. An event's light cone consists of two parts: the future light cone and the past light cone. The future light cone encompasses all possible locations that a light signal emitted from the event could reach, while the past light cone encompasses all possible locations from which a light signal could have arrived at the event. Events within the future light cone can be causally affected by the event in question, while those in the past light cone could have causally influenced it. Events outside this light cone are said to be space-like separated, meaning they cannot influence each other because it would require information to travel faster than light, violating relativity. Crucially, the speed of light enforces a universal limit on how fast information or causal effects can travel. This ensures that the order of events remains consistent across different observers' frames of reference, preventing paradoxes such as receiving information before it was sent. For instance, if information were transmitted faster than light, one could receive a message before it was dispatched, thus enabling scenarios that conflict with our intuitive and physical understanding of causality. This relativistic check on causality preserves consistency across space and time. Consider two observers moving relative to each other. Using the Lorentz transformations, the mathematical formulations underpinning special relativity, both observers would agree on the sequence of causally related events within each other's light cones, despite differing in their measurements of time and space. This agreement underscores how the speed of light maintains causal order across varying reference frames. In scenarios like gravitational waves or synchrotron radiation, causality ensures that effects propagate outward at the speed of light. For gravitational waves, distortions in spacetime emanate from events like merging black holes at light speed, ensuring a consistent causal relationship with detectable effects on Earth. Similarly, in particle accelerators, synchrotron radiation, the electromagnetic radiation emitted when charged particles are accelerated, adheres to relativistic constraints, ensuring no causal violations. Quantum entanglement, while exhibiting what appears as instantaneous correlations between spatially separated particles, does not violate relativistic causality. This is because while entangled particles affect each other's states instantaneously, no usable information travels faster than light, preserving the overarching causal structure dictated by relativity. In summary, the constancy of the speed of light is integral to upholding causality in our universe. It ensures that cause and effect relationships remain consistent and invariant across different frames of reference, thus maintaining the logical structure of physical laws and preventing paradoxes that would arise from faster-than-light interactions. This fundamental principle continues to be a cornerstone of both theoretical and experimental physics, guiding our understanding of spacetime and the universe. Light cones are a fundamental concept in the realms of cosmology and theoretical physics. Imagine spacetime as a grand tapestry where every event, every moment in time, and every point in space exists. At any given moment in an object's life, its potential future and immutable past are described by a structure called a light cone. Picture a flashlight in the dark, its beam expanding outward. In spacetime, the light cone expands from a single event, illustrating the limits within which light, and hence any causal signal, can travel. The light cone is divided into two parts. The forward light cone opens up from the event, encapsulating all possible trajectories light could take from that point forward in time. This defines the realm of possible future events that can be influenced by what happened at the tip of the cone. Conversely, the backward light cone contains all the paths that light could have taken to converge upon that specific event, spanning its entire past. Events outside this cone cannot affect or be affected instantaneously by the event inside the cone, respecting the universal speed limit set by the speed of light. This elegant structure is not just a theoretical visualization, it encapsulates the very essence of how events are interconnected in the fabric of our universe, providing a powerful tool for understanding causality in cosmological models. Black holes, enigmatic and captivating, exert a profound influence on the path of light and our broader understanding of relativity. According to Einstein's theory of general relativity, massive objects can warp the very fabric of spacetime. Black holes, with their immense gravitational pull, distort spacetime to such a degree that even light cannot escape their grasp once past a certain threshold known as the event horizon. This boundary marks a point of no return. Beyond it, not even light can escape, rendering the black hole essentially invisible against the backdrop of space. When light passes near a black hole, its path bends, a phenomenon known as gravitational lensing. Imagine shining a laser pointer through a curved glass. The light doesn't travel in a straight line anymore. Instead, it follows the contour of the glass, changing direction. Similarly, the light's trajectory near a black hole curves dramatically, often forming arcs or even rings to an outside observer, famously captured in what we call Einstein rings. This bending of light provides a unique way to observe and study black holes indirectly, offering a critical tool for astronomers to detect these otherwise elusive objects. These effects reinforce the core principles of general relativity, which posits that mass and energy directly influence the curvature of space-time. Black holes serve as extreme testbeds for these principles, allowing scientists to explore the boundaries of our physical theories. Observing how light behaves in the presence of a black hole not only affirms our current understanding, but also pushes the envelope, prompting questions about the very nature of space-time and paving the way for new discoveries in theoretical physics. The twin paradox is a thought experiment in special relativity that highlights the startling effects of traveling at speeds close to that of light. Imagine two identical twins. One twin remains on Earth while the other embarks on a journey through space at nearly the speed of light. According to the principles of special relativity, time dilation occurs for the traveling twin. Time effectively slows down for them compared to the twin on Earth. After several years, when the traveling twin returns home, they discover something astonishing. Despite what felt like a shorter journey to the traveler, the twin who stayed behind on Earth has aged significantly more. This isn't merely science fiction, but a real consequence of Einstein's theories. The paradox emerges because, superficially, each twin could argue that they were the one who remained stationary while the other moved, leading to some confusion about why they should age differently. However, this conundrum is resolved through general relativity, which accounts for the acceleration and deceleration phases of the traveling twin's journey, distinguishing their experience from the twin who remained in an inertial frame on Earth. The twin paradox isn't just an intriguing puzzle, it's a profound illustration of how relativity reshapes our understanding of time and space. It underscores that time isn't a constant, unchanging backdrop, but a dynamic, malleable dimension influenced by relative motion and gravity. This effect has been experimentally confirmed with precise atomic clocks placed on fast-moving aircraft or satellites, where the clocks indeed tick slower compared to those on the ground. The twin paradox captures the essence of relativistic time dilation, demonstrating that our intuitive grasp of time must adapt to the extraordinary realities of the cosmic scale. Relativity revolutionizes our intuitive understanding of time and space, fundamentally altering concepts we once considered absolute. In everyday life, we treat time as a constant march and space as a fixed backdrop against which events unfold. Yet, Einstein's theories of relativity, both special and general, demonstrate that time and space are interconnected, dynamic, and influenced by motion and gravity. This union of time and space into a single continuum known as spacetime overturns classical notions and introduces a more fluid, interconnected reality. Special relativity, for example, introduced the concept of time dilation, where time slows down for objects moving at significant fractions of the speed of light. Imagine a spacecraft hurtling through space. On board, the passage of time would slow relative to an observer on Earth. This isn't merely theoretical, it's a real, measurable effect confirmed by experiments, such as those involving high-speed particle accelerators and precise timekeeping on fast-moving jets. Additionally, length contraction asserts that objects in motion shrink along the direction of their velocity, redefining our understanding of shape and distance. General relativity takes these ideas a step further by incorporating gravity. It posits that massive objects like stars and planets curve the fabric of spacetime, and this curvature affects the motion of objects and the flow of time. Near a massive body like Earth, time ticks slightly slower compared to higher altitudes, a phenomenon verified by GPS satellites, which must account for these discrepancies to provide accurate positioning data. Gravity, in this sense, isn't simply a force pulling objects together, but a curvature of spacetime itself, directing the paths objects follow. Together, these insights challenge our perception, revealing that the universe isn't a rigid stage but a malleable entity where space and time are intertwined and mutable. They unveil a cosmos far more intricate and interconnected than previously imagined, revealing the profound beauty and complexity of our universe. The practical applications of relativity extend far beyond theoretical physics and have become integral to numerous modern technologies. One of the most prominent examples is the Global Positioning System, GPS, which we rely on for navigation in our daily lives. GPS satellites orbit the Earth at high speeds and significant altitudes, where both special and general relativity come into play. Due to their high velocity, time on board these satellites runs slightly slower compared to clocks on the Earth's surface, a consequence of special relativity. Conversely, because they are farther from the Earth's gravitational well, time runs faster for these satellites according to general relativity. The combined effect of both these relativistic time dilations is critical for maintaining the precision that allows your GPS to pinpoint your location accurately. Another fascinating application of relativity is in the realm of telecommunications. Signals sent through space, from satellite relays to ground stations, are affected by relativistic effects. Accurate timing is imperative for synchronization in the transmission and reception of data. Even fiber optic communications, which send data through light pulses, must account for relativistic corrections to ensure data integrity over long distances. Furthermore, in the domain of astrophysics and cosmology, relativity provides the backbone for technologies such as the Event Horizon Telescope, EHT. The landmark event of capturing the first image of a black hole's event horizon wouldn't have been possible without the understanding of spacetime distortions predicted by general relativity. This technology allows scientists to verify theoretical models and explore phenomena like gravitational waves, ripples in spacetime caused by cataclysmic events, detected by instruments like LIGO and Virgo. These detections not only enrich our comprehension of cosmic events, but also have practical implications for understanding fundamental forces and particles here on Earth. Einstein's theories of relativity don't merely reside in the abstract realm, they underpin technologies that drive modern conveniences and scientific missions, enhancing our daily lives and expanding the frontiers of our cosmic understanding. The curvature of spacetime, as delineated by Einstein's general theory of relativity, profoundly influences the travel of light throughout the universe. In the presence of massive objects like stars, planets, and black holes, spacetime itself is warped. Light, which typically follows a straight path in the absence of gravity, must instead traverse these curves and bends. This phenomenon, known as gravitational lensing, makes light bend around massive objects, resulting in fascinating and often beautiful distortions of background astronomical objects. Imagine light as a river flowing through the landscape of spacetime. In flat space, the river runs straight and unimpeded. However, in curved spacetime near a massive object, the river twists and turns, flowing around valleys and hills. Similarly, light from a distant star will warp around an intervening galaxy cluster, sometimes producing multiple images of the same celestial object, or even creating rings of light known as Einstein rings. This effect isn't just a cosmic curiosity, it serves as a powerful tool for astronomers. By studying these gravitational lenses, scientists can infer the presence of dark matter, map the distribution of invisible mass, and even measure the universe's rate of expansion with extraordinary precision. The curvature of spacetime leads to phenomena like gravitational redshift. As light climbs out of a strong gravitational field, it loses energy, resulting in a shift towards the red end of the spectrum. This is akin to a ball rolling uphill, gradually slowing down and losing some of its kinetic energy. Observing this shift allows astronomers to gauge the gravitational strength of massive celestial bodies, contributing to a deeper understanding of their properties and behaviors. Altogether, the interaction between light and curved spacetime enriches our scientific narrative, enabling us to explore the unseen and understand the complex interplay of mass and gravity. Through these effects, light narrates the history and structure of the universe, revealing the potent influence of general relativity on the vast cosmic stage.